Thank you. Good morning, everybody. Thank you for joining us today for building carbon removal ecosystems in the Global South. Today's conversation is really about something bigger than any one technology. It's about how we build complete ecosystems, linking science, infrastructure, workforce, and policy to enable durable carbon removal at scale. So the question we're asking today is, how do we build these ecosystems in ways that are regionally grounded, scientifically rigorous, and globally connected? And importantly, how do we ensure that this transition builds local capacity, creates economic opportunity, and reflects the unique resources and strengths of each region? My name is Jennifer Wilcox. I'm a professor here at the University of Pennsylvania. I know many of you who are here today in the audience, but also brought a really eclectic group of speakers today that I'm really excited about for this webinar. We've structured today's discussion in three connected parts. First, we begin with engineering and geological foundations, understanding the physical systems that make durable carbon removal possible across regions like Brazil, India, and Kenya. Second, we move into systems and deployment, focusing on the role of industry and government in shaping infrastructure policy and investment pathways that determine which carbon removal approaches can scale in different regions. And third, we focus on how carbon removal fits within the broader climate strategies, how it complements, not competes, with decarbonization to achieve net zero targets, and how emerging voluntary and compliance markets are creating new opportunities globally. Every region has something to offer, whether it's suitable geology for storage, sustainable biomass resources, or abundant renewable energy, including wind, water, solar, and geothermal. Across all three sections, a few themes connect everything that we'll hear today. Regional resource advantages matter. Basalt formations in India and Kenya, enabling CO2 mineralization. Brazil's deep expertise in subsurface CO2 management. Energy systems shape technology choices. All electric direct air capture paired with wind and solar. Geothermal enabled direct air capture in places like Kenya. Biomass to fuels coupled with CCS. And ultimately, people and institutions determine success. Universities training the next generation, knowledge transfer across regions, workforce development rooted in local contexts. To help bring these perspectives to life, we've structured today's sessions to be interactive and discussion-driven. Each session will be opened by a member of my team at Penn who will introduce the speakers. Moderators are research associates and PhD students from my group who will also help to field questions and guide the discussion. We encourage you to submit questions using the Q&A feature or chat. And for our speakers, we kindly ask that you keep remarks to about 10 minutes so that we have time for conversation. So with that, let's begin with our academic speakers who will ground us in the science, geology, and engineering foundations that underpin everything that we'll discuss today. Our first speaker is Fabio Toniolo, who is a professor of chemical engineering at the Federal University of Rio de Janeiro. His work focuses on catalysis, biomass valorization, and CO2 conversion, helping us understand how carbon removal pathways can integrate with Brazil's renewable energy systems and industrial landscape. And I'll turn it over to you, Fabio.
Okay, I open my microphone and okay, can you see the entire screen?
It looks perfect.
Okay, so thank you so much, Jennifer, for the kind invitation and introduction. Today I'll talk a little bit about CCUS hubs and SAF opportunities. As you know, CCUS means carbon capture, utilization, and storage. And SAF is sustainable aviation fuels. So the idea here is connecting opportunities for the creation of CCUS hubs and SAF scaling up in Brazil. Um, I would like to present a very interesting assessment carried out by S&P Global Agency, supported by Petrobras, which is the Brazilian uh, oil and gas company. And this study was published 2 years ago, and it's actually the first national multidisciplinary assessment that takes into account many challenges related to the CCUS hub creation. So it takes into account engineering, geology, emissions, infrastructure, economics, financial, and technical challenges. And this study strengthens the low carbon competitiveness for Brazilian steel and other export sectors. And it highlights how catalysis is a very important field in science to make possible the conversion of CO2 into fuels and chemicals, and which promotes the industrial can promote the industrial decarbonization. So this study highlights the regions in Brazil that are very promising for the creation of CCUS hubs. So what are these hubs? This is the Brazil map. We here we have the 26 states, but this study uh, uh, grouped the different states in regions which are connecting like the industry, the logistic, and the opportunities for the CCUS. So the number one, as this region number one in dark blue, is the southeast area in Brazil. It includes three states: Minas Gerais, Rio de Janeiro, and Espírito Santo. I live and work in Rio de Janeiro, and we are located exactly in this area number one. So the this area it is responsible for the highest production of CO2 emissions in the country, especially because of the industry concentrated in this area. So the study indicates that the area number one and the area number two form a corridor very important for the creation of CCUS hubs and give us as a country the opportunity to think in possibilities of capturing the CO2 and transforming in more valuable compounds. Uh, and the area number one is responsible for 36% of CCUS opportunities. And it happens because in the southeast area, we have a huge concentration of industries like cement industry, iron and steel, and refineries. This area is responsible for the emission of 37 megatons of CO2 every year. And the area number one and two are also the most developed uh, areas in Brazil in terms of research and development, innovation, and oil and gas companies, and includes and actually concentrates the most important universities and research centers in the country. The southeast area, all that corridor in areas number one and two, are also very important areas for the production of biofuels in Brazil. So that's interesting to connect the CCUS opportunities with the biofuel productions. So the Southeast Corridor in Brazil concentrates industry, logistics, and aviation flows. And as you know, Brazil is a big producer of ethanol from sugarcane. And this high potential of Brazil in terms of ethanol production is very important when we think about converting ethanol into more valuable products. And I would like to emphasize the sustainable aviation fuels. So we have in Brazil the opportunity to connect the industrial hubs with the scaling up of processes for sustainable aviation fuels. And that will make us possible the creation of a national platform for decarbonization in the country. So nowadays in Brazil, we have these four big initiatives for the production of sustainable aviation fuels in large scale. The first one is located in north of Brazil. This biorefinery will be producing this year 500 million liters of SAF per year, and it would be produced from vegetable oil. Another initiative in northeast of Brazil is the number two in Marataípe, Bahia. It will be producing also SAF from vegetable oil, and other two initiatives will be operating in the future in southeast, in São Paulo, and two of them are in São Paulo state. But for example, in Rio de Janeiro state, where I live, we don't have any initiative for the production of SAF in large scale. So that's actually insane because we are located in the middle of the main ecosystem for CCUS hub. And we need to start thinking in opportunities to, for example, in creating pilot plants for SAF production. The main airport in Rio de Janeiro is Galeão, and last year it conducted the first SAF importation. So that's crazy because we are importing, we are buying SAF from other countries, but we still don't produce it. And the refineries around Rio de Janeiro, they are already certified to produce SAF, but we still need to uh, create the pilot plans. We need to create the opportunities to produce SAF in large scales. So the message here is that the southeast of Brazil is still have a lot of opportunities to develop um, uh, CCUS opportunities. So Brazil and Southeast regions has the science, the industry, and the strategic position for CCUS hubs. And as a country, you have the opportunity to lead the next generation of low carbon fuels and chemicals. But we still have a lot of to do, and we need to do that in collaboration inside the country and outside, of course. That's the reason we are here discussing and thinking in the opportunity of making difference. So to finish, I would like to mention that I work and lead a catalysis group in the Federal University of Rio. We develop catalytic materials and reactor engineering. We work with petrochemical processes and companies, national and international companies. We work with hydrogen production. We have been working very hard with the catalytic conversion of biomass and CO2 into valuables compounds like fuels and chemicals for industry. And we work from the atomic scale to the scaling up for industry because our concern is developing new materials and apply it until the industrial application. This is our group. We are more than 40 people, including PhD, master, and undergrad students. And these are our international and national collaboration with universities, with companies, and we have, of course, initiatives for teaching and research. This is my email address and WhatsApp and WeChat contact. Thank you so much for the opportunity. I'll stop now my screen.
Thank you so much, Fabio. We will hold all of the Q&A for the end of the panel session. But for the audience, please do put any questions that you have using the Q&A function at the bottom of your screen. It's a little box with a question mark. And we'll move on to our next speaker. Our next speaker is Colombo Tassinari. He is a professor at the University of Sao Paulo's Institute of Energy and Environment. He brings deep expertise in geological storage with a focus on Brazil's sedimentary basins and the subsurface characterization required for durable CO2 sequestration. Colombo, I'll pass it over to you.
Okay, good morning to everyone. First of all, I would like to thank Jennifer by this invitation, the opportunity to be here. Today, my presentations will be about CO2 geological storage in Brazil. We will analyze some potential for BECCS and the geologic storage opportunities.
You might put it on slideshow mode. I think you're in the notes now, Colombo.
Sorry?
Could you put it on slideshow mode? The little symbol at the bottom of your PowerPoint.
The slide change now?
It's in the notes version. Like if you go to the bottom right of your screen, the little symbol.
Oh, okay.
Perfect. Thank you.
Now it's better?
It's beautiful.
Okay. Well, in this map, we can see the distributions of the main CO2 emission sources in Brazil. And it's possible to see that in the north part of the country, we have several diesel and gas thermal power plants. In the southeastern Brazil, we have mainly bioethanol plants, fertilizer plants, and also pulp and paper mills. Okay? And in this another map, we have the distributions of the Brazil's major sedimentary basins. We know that sedimentary basins include the best sites for CO2 geological storage. And in Brazil, we have a large areas covered by sedimentary rocks, like you can see in this green color. We have several onshore sedimentary basins, but also offshore sedimentary basins, which include the major oil fields in Brazil. Okay? And we have in the Amazonas, for example, Parnaíba sedimentary basins, Parecis, São Francisco, and the Paraná sedimentary basins that are the most important sedimentary basins in our country. If you compare the distributions of the main CO2 emission sources, it's possible to observe that in the north part, we have a lot of diesel, mainly diesel, but also gas thermal power plants within Amazonas sedimentary basins. In the southeast part of the country, we have the measures of CO2 emission sources related to the Paraná Parecis sedimentary basins. And the most of the CO2 emission sources are bioethanol plants, included this triangle, the green triangle here. Okay. Well, the major opportunities for CCUS projects in Brazil, we have several, but in my opinion, we have one. It is very important, associated with thermoelectric diesel power plants where in Amazonas sedimentary basins, where the geological reservoirs are, for example, could be saline aquifers, basalt rocks, and also black shales. The second opportunity is related to the oil extractions in the offshore sedimentary basins, which we have and depleted oil and gas field to use as CO2 geological reservoirs. We have associated with this depleted oil field saline aquifers, and also we have a very important project for EOR developed by Petrobras in the Santos Basin, located in these regions, where we have the large oil fields of the pre-salt zones. And another one is related to BECCS, Bioenergy with CCS, in the Paraná, Parecis sedimentary basins in southeastern Brazil. Now I will focus in BECCS, and the productions of bioethanol is carbon neutral because the sugarcane absorbs CO2 from the atmosphere, and in the bioethanol plants, the sugarcane is burned, the CO2 is released again to the atmosphere, the same CO2. So this process, bioethanol productions, is carbon neutral. But if instead of to release the CO2, we transport the CO2 for geological storage, for example, like this, the bioethanol plants will produce negative CO2 emissions. In other words, bioethanol plants will contribute to the reductions of the amount of CO2 within the atmosphere. Okay? The bioethanol productions in Brazil is a very important business. In São Paulo state, for example, the sugarcane ethanol productions only in São Paulo state is around 13.5 billion liters. This corresponds to 13% of the world's bioethanol productions, considering sugarcane plus corn. And the total of CO2 emissions in the 24-25 harvest, for example, in São Paulo states, were about 120 million tons. Okay? So the productions of bioethanol is very important. And we have here in São Paulo one science and technology center for BECCS development to try to develop technologies to produce negative CO2 emissions in the Brazilian bioethanol industry. This center is supported by FAPESP and also by Petrobras, the Brazilian oil company, like you see in the talk before. And this map shows the distributions of the Brazil sedimentary basins, including CO2 emission sources. And it's possible to see that in the southeastern part of the country, mainly in São Paulo state, we have very important concentrations of bioethanol plants just within Paraná sedimentary basins. This Center of Science and Technology Development of CO2 capture and geologic storage have as objective evaluated the feasibility of implementing a hub for geologic storage of CO2 captured from bioethanol plants in the state of São Paulo. It's a multidisciplinary project involving engineering, about infrastructure and the development of new technologies, geology, geophysics to selections the best areas and the reservoir characterizations, and also regulations and society part to establish la regulamentations of the BECCS activity. Here you can see a map, a geological map of the Paraná Sedimentary Basin. It's possible to see the area in the country which are covered by Paraná Sedimentary Basins. This is a geological profile of in the connect A and B points, where it's possible to see, for example, basalt layer, very important for CO2 geological reservoirs, and in green color, saline aquifers, and also black shales. Okay. These sedimentary basins has around 3,000 kilometers in length and about 7 kilometers depth in the central part. Here only to see the potential geological CO2 storage sites for BECCS in the stratigraphic column of sedimentary basin. We have basalts, is very thick, extensive lava flows in south part. We have also black shale, where we can store CO2 together with the productions of blue hydrogen, for example, and we have saline aquifers and unminable coal seams. That is my email. I am a geologist, and I work in the Institute of Energy and Environment of the University of São Paulo. Thank you for your attention.
Thank you so much, Colombo. We will transition to our next speaker. Celio Cavalcante is a professor of chemical engineering at the Federal University of Ceará. His research focuses on adsorption materials, advancing direct air capture technologies, and role in emerging carbon removal ecosystems. Celio, I'll hand it over to you.
Thank you, Jan. I'm trying to start sharing the screen. Let's see. It worked earlier, so it should work now. Can you see my screen?
Yes, you just need to put it on slideshow mode.
Okay.
It looks perfect.
Okay, that's it. So, good morning, everyone, or good afternoon, or even good evening to some. We are at the University of Ceará in Brazil, and I want to thank again Jen for the opportunity to share some of our work and the possibility to join this great initiative by the Kleinman Center to bridge all the different interests and subjects into this panel and possible future collaborations. So we are here in Fortaleza. I don't know if you can see my mouse. The equator is right across the street from where I am now. So it's interesting because we saw a talk from the high industrial session in Brazil, which is the southern part, southeast, for people in Rio and São Paulo. And I would say Brazil can be divided basically in three big areas regarding the CO2 subject. There is an area that emits a lot of CO2, that's the industrialized part. There is a huge area, which is more than half of the country, that removes CO2, that's the Amazon forest. And there is this northeast part, which is a highly renewable energy region, because here, as Jen saw when she visited us some months ago, we have lots of sun and wind. So it's now it's a very productive, low carbon energy producer in this area. And we are in this research group for adsorption. This is a picture of our entrance of our lab. And we basically focus on three aspects of all related to adsorption, which is the fundamentals, the characterization of the materials, and processes. So we try to align material science and process engineering to reach some viable processes. In this case, we have other interests as well, but in this case, for carbon capture and utilization. The group of 4 faculty members. The main coordinator is Diana Azevedo. She is in the audience as a participant. And Moisés leads the day-to-day base of our gas adsorption lab. And I'm on my way out, being the oldest, and along with another colleague who is an emeritus professor. So this is our group. We have several researchers and postdocs researchers and several graduate students and research technicians, and another maybe 30 undergraduate students involved in this area. Our infrastructure, very briefly, we are well equipped, I think, to develop adsorption studies. This is mainly based on these slides on systems for gas separations, especially, or gas reactions. As we can see here, I'm not going through all of them, but we have everything to characterize nanoporous materials. We have a system for aging catalysts in some specific projects with Petrobras, for instance. And we have systems for adsorption direct measurements, magnetic suspension balances. From Rubotherm, we have a fixed bed automated system for multi-component adsorption in dynamics measurements, microcalorimeters, a lab scale PSA, pressure swing unit. And in general, our projects are within these 3 big boxes here: gas separations and purifications, materials development, reaction engineering. And under this box, I will share the slides later with Bill. So I think it will be available to everyone. And so that I don't have to go through every detail of these slides, but in general, we work with several aspects of carbon capture, oxygen production, biogas, CO2 conversion, methanol, DME. And I take this slide from Avram Rajendran's famous paper that we try to cover this area here in this process development from adsorbent to the process, to the final process evaluation, from where we can go to the industrial application. So we go from milligrams or grams of materials to characterization using tens of grams, between 10 and 100 grams, and at the final level to kilos, to a pilot or prototype kind of testing. So with different interests in each of these steps, from knowing the material to evaluating purity, recovery, energy, scheduling, costing, going through process modeling, simulation. That's all written there. So this is a summary of our general R&D topics that we've been working on from CO2 capture in thermal plants, and using movie bed temperature swing adsorption. We have been involved in hydrogen storage because of this plenty of abundance of solar and wind energy here. There's a big interest, a big push from our local government to have hydrogen applications from electrolysis. And also we have some studies with Petrobras on natural gas dehydration using adsorbents. Okay, very quickly, we have a project that's being developed for the last maybe 5 to 6 years that involves a pilot scale plant for flue gas carbon capture. So this is a picture of the pilot scale plant. This is not at UFC. This is at an industrial academic group in Santa Catarina, in Criciúma. They built this pilot plant, and we worked alongside them to measure the fundamentals, the absorption fundamentals, and the process estimations. This obviously involves using zeolites to remove the CO2 from flue gas. This is not direct air capture. And this has been funded by a thermal plant, a Brazilian thermal plant. That's a company called Eneva. And we have other projects that I'm not going into detail here, but the slides will be available, involving materials for temperature swing absorption for CO2 capture, for CO2 removal, relating the nitrogen content with absorption properties. So this is a hybrid materials trying to remove the CO2. So this is amino materials, amino functions on mainly carbon, activated carbon adsorbent. We also have using 13X from flue gas, using temperature swing adsorption. Along with each of these topics, there are papers that's been published by our group. So in general, it's just these are the type of experiments we do, trying to relate the adsorption properties with the desorption, with the fundamentals of isotherms and kinetics. So on that work with the pilot scale, we did with the moving bed temperature swing adsorption, we did studies, parametric analysis. This is what we call in process modeling design, that we can estimate the amount of energy that we can save on using this. And we compared the results with amine absorption. That's the main process still used in industry for flue gas recovery, removal. And lately, we've had papers in studies in machine learning and adsorption process that was cover of industrial engineering chemistry research, applied to optimization, to process optimization, in this case of gas adsorption. And also with artificial intelligence, trying to apply this for the guideline for direct conversion of CO2 to dimethyl ether, recently published also. Some of the results are summarized here. This was a collaboration with the Yonsei University in South Korea. And more recently, due to this interest in sustainable energies, UFC is leading a research consortium trying to bridge, to put together all the different aspects of sustainable energies, which involves as CO2 recovery and capture and conversion as well, involving in our state, in our research center, in our state research funding agency. And also led by Diana, we have a consortium national-wise with several academic institutions from different parts of the country. São Paulo, I think this one is also in São Paulo, São Carlos, and Sergipe. And here we show different in Santa Catarina, and some international universities in the United States, Canada, Spain, and I confess I don't remember this one. I think it's France. Oh, okay. And looking at the direct proposition of this talk, of this panel, in Brazil, I would say there's still no DACCS specific regulation, so we think it's a good thing to be maybe a first mover for developing technology, and I hope we can breed from other panelists in this area. But we have abundant low carbon energy, which is from solar, wind, and biomass. In our region, it's mainly solar and wind, but biomass in other parts of the country, which is critical for the non-competitive, for cost-competitive DACC. Brazil has a big, as the previous speakers have said, oil and gas infrastructure. So, as the professor from USP mentioned, we can have CO2 storage, and there is a very good infrastructure for that. So we have, I think, a strong R&D base in adsorption materials and structural reactors, a synergy with the hydrogen economy that's been brought up in the last few months. So we think we can position to maybe pilot scale DACC and evaluate more advanced sorbents. In this aspect, we just started last year, at the second semester. We received samples from a colleague in other group in international, and we did some preliminary, I call it very preliminary studies using the fixed bed automated system at very low. It's not with flue gas we have high concentration. Here we're talking about 600 ppm up to maybe 4,000 ppm, but we could have this measurement. So this just shows a capability of doing this. This was the condition that we used with air and CO2, and this is the adsorbed amount that we could measure using this experiment. This is air plus CO2. So to finalize, we have to say this is not by ourselves. We have several international partners and Brazilian partners here. So we want to fill some more of these squares here with people from this panel. And our funding comes mainly from government agencies, the Ministry of Science and Technology, some companies, Petrobras and Eneva, and the state funding agency. There are several others, but we just show here the main ones. And here I show a very smiley group here, very sunny. Fortaleza is a very sunny place. And our contacts are shown here. So please, when you have the opportunity, share your views and comments with us. With this, I close this, and I thank again Jen and Bill and the Kleinman Center for this opportunity.
Thank you so much, Celio. Fantastic. We'll transition to our next speaker and also transition over to India with Professor Vikram Vishal, who is a professor in the Department of Earth Sciences at IIT in Bombay. His work focuses on geological carbon storage, particularly with basalt formations, an important pathway for permanent CO2 sequestration in India. Vikram.
Hi, Jen. Thanks for the introduction and for the invitation again. Can you please confirm if the screen is visible and am I audible properly?
It looks perfect, Vikram.
Great. Thank you so much once again for the opportunity, and glad to connect with other fellow experts from around the world and especially Global South. My name is Vikram Vishal, and I am a professor in the Department of Earth Sciences at IIT Bombay. And I also head something called as the DST's National Center of Excellence in CCUS, hosted at IIT Bombay. And if it's a national center and it's a center of excellence, so we focus across the verticals of CCUS, whether it is capture, carbon dioxide utilization, or carbon dioxide sequestration, and the cross-cutting systems. So this is the first such center of excellence supported by the Ministry of Science and Technology in the Government of India, established in 2021. This is a landmark year for us because in India, the first time the Honorable Prime Minister announced the net zero goal for the country, which is 2070. And it was announced in Glasgow in November 2021, and December, the center was launched. So it's very timely from that point of view. And we have 22 faculty colleagues who are working across different domains. So we do understand how CO2 is captured, but can we have new methods of capturing carbon dioxide or improve the existing methods of capturing carbon dioxide? We have processes for conversion to different chemicals. Somehow in India, there's a lot of push on CCU, whereas globally we do understand that utilization pathways are limited. but then there is a lot of clarity that there are pathways which can offset the cost of doing CCU in the first place, and therefore utilization is being pursued with more seriousness. Having said this, we do realize that India emits around 3 billion tons of carbon dioxide annually, and we have not yet peaked our emissions yet. So definitely we'll be adding more and more carbon dioxide annually, and therefore geological sequestration becomes inevitable. And we'll go one step ahead and say that even that may not be sufficient. So we have to look at the engineered pathways for carbon dioxide removal, and therefore in that case also putting carbon dioxide into basalt formations and saline formations becomes very inevitable. So we received a lot of support from different industries as early founding members to this National Center of Excellence. So it's not an academic center alone. It is focused, its very foundation is research and translation of research with the industrial support. And that's where it becomes very, very unique. A bit on the capture side as well, because when I returned from Stanford after completing my stint in postdoc with Professor Jennifer Wilcox in 2016, it was very early for India to talk about CCU and CCUS. So therefore, I was able to convince the top management of India's largest power producing company, which is NTPC, National Thermal Power Corporation earlier, now NTPC, and looked into the feasibility of capturing carbon dioxide and converting to different chemicals. So we delivered very detailed reports and information for such process. And based on this study in 2022, NTPC set up India's first CO2 capture and conversion plant in another part of the country. So from a very, so to say, a stand which was not at all towards CCUS, it changed for the largest thermal power corporation, and Ministry of Power became nodal to a lot of activities that happened thereafter. So we looked at the technologies also where we are capturing carbon dioxide. So at IIT Bombay, as researchers, we found a unique way of capturing carbon dioxide, which can take CO2 from the air as well as from the industrial flue gases, and it dissolves the carbon dioxide in water. Now, this water is wastewater, seawater, RO reject water, any kind of industrial wastewater that we get, and it dissolves carbon dioxide in an accelerated way. So we have a catalyst which essentially mimics the enzyme in our body called carbonic anhydrase. And this is essentially a catalyst, a chemical compound, so it can withstand the harsh conditions of the industries also, and accelerates the dissolution of carbon dioxide in water. And we are able to bring the calcium carbonate out by adding any source of cation which can precipitate, let's say, calcium carbonate, magnesium carbonate, and so on. We have even gone ahead and used seawater and precipitated sodium carbonate and bicarbonate by, of course, high concentrated solutions, and then got the salt out. So we are looking at pathways where we can do away with the amine-based capture totally and get into these kind of methods of capturing carbon dioxide. And you may see that this is a small direct air capture system that we set up using this technology. And this technology also received the CCS X Prize from the X Prize and Elon Musk Foundation early in 2021 itself. And we set up a plant which is based on this kind of a technology, which you can see it's a very small plant compared to many of the other plants. Of course, the blowers are outside. So this becomes the first such facility in India to sell carbon dioxide credits based on direct air capture technology, also indigenously developed and scaled up. Now we look at where exactly are the large point sources of emissions in India. You're able to see the map of India, and different sectors are reflected, such as steel, cement, power plants, refineries, biomass plants, fertilizers, and so on. You can see that across the country, which is a huge landmass, there is complete distribution of large point sources of emissions. So how do we figure out that where we can capture the carbon dioxide from, and can we make a common transportation infrastructure in a hub and cluster model for CO2 capture in the Indian context? So the question essentially comes, we know that we have a large point source of emissions, but where do we have the sink spaces for carbon dioxide in India? And that brings me to the domain that we specialize on, is on geological carbon sequestration. You see again the map of India. There are different colors that you're able to see. So the orange color indicates the bubbles are indicating the sedimentary basins in India which are producing oil and gas. So a large number of fields are in the depleting stage, so or rather depleted, declared. So we can target them for storage of carbon dioxide, just to put the CO2 inside. Because we have a lot of familiarity with those reservoirs because of years of, or so to say, decades of exploitation of those reservoirs. We have a lot of data and samples. So these become the low-hanging fruit for trying out CO2 injection in India. Having said this, if you can see these, the blue bubbles all around, these sedimentary basins, these are the saline formations in the sedimentary basins in India. We have 26 sedimentary basins in India, and we map the CO2 storage potential in these places as well. In these boxes that you're able to see, these are the basalt locations for India. And the numbers here are indicating in terms of gigatons of CO2 storage potential in India. So we can see that if we go with different pathways, the maximum amount of CO2 can be stored in the onshore and offshore saline aquifers in India, as well as the basalt formations from somewhere from 97 to 316 gigatons of carbon dioxide. All in all, India has a potential of roughly 400 to 600 billion tons of carbon dioxide storage potential across different strata in India. This work also comes from our group and interestingly also published in 2021, very timely in terms of India's ambitions to achieve net zero, and this was released. Then we tried to bring the hub and cluster concept. So we know how, let's say, the Northern Lights in Norway is a clear example of geological sink being made available to other stakeholders from other countries, and it can be transported. But given in India that we have more than surplus sources of carbon dioxide, so can we in that case link these carbon dioxide sources? So you see these bubbles are drawn on those 7 sedimentary basins which are producing oil and gas. So we have a lot of data, as I mentioned, so we are targeting them as low-hanging fruit, whether it is offshore of Mumbai to Gujarat, Cambay Basin. And these circles are indicating distance from the Euclidean center of these basins and how many point sources of emissions can be covered in this. So you can see that there is substantial number of CO2 sources in each of these bubbles, and we can formulate, therefore, some 13 hub and cluster model, where the hub is the storage space and cluster is the sources of different carbon dioxide sources such as steel, cement, power, and so on. And this is also giving clarity that each region can have their own sources of carbon dioxide. They can be linked for storage in different formations. So based on this, we carry out very detailed. So that was more like an umbrella assessment countrywide. Now we are zooming into regional data audit, which is again from the Western India, where very likely the first CO2 injection in a saline formation or a depleted oil fields is likely to happen. So based on the published data and national repository data, we got the data and we identify the sites. We are doing the site characterization. We have a fairly state-of-art laboratory where we characterize the samples in different CO2 flow conditions and include them in the model. And then a detailed dynamic model is created with scenarios of placing the CO2 injection wells and into cutting across these strata. These strata are around 1,500 to 2,300 meters deep from the surface. So it goes really deep, and so we need to understand the subsurface very well. And the most important aspect of our research group is to do geomechanical risk assessment. In the end, no cap rock should be breached, the integrity should not be breached, and the long-term security of CO2 injection should be ensured. So that is something that we carry out. So from the very countrywide assessment to very zoomed in layer by layer simulations and understanding is brought in terms of the study that we are doing. To add to this, in one of the sedimentary formations, the country's first CO2 injection well was also drilled based on the efforts from IIT Bombay. You can see that the rig was placed and we drilled 3 wells, which are around 1,200 meters deep, to identify sedimentary strata and core formations, which are deeper than 800 meters that could be target for CO2 injection. You see that we have a lot of patronage from the government agency. Niti Aayog is the policy think tank of the government of India. A bit on the Deccan basalts. Of course, we have a fantastic speaker later in the queue from India to talk about the basalts more specifically. But I want to give you a sense that the map of India, that we have a huge expanse of basalts in the country. Deccan basalts alone, is spread across 500,000 square kilometers. And if you take an average of 1 kilometer thickness, it's 500,000 cubic kilometers of the basalt that is available. So in that case, there's a huge potential for CO2 storage in basalts. This is what you're seeing on the surface, the topography, but in the underground, as you go deeper, lots of basalts exist. And in the western part of the country, we have as deep as 6 kilometers thickness of thick basalt formation. So for geological sequestration, it is a good possibility. But we also know that basalt is taken as a construction material, and a lot of basalt is actually fines are wasted, and it's a difficulty to dispose them. So can we extend those waste basalts from the mine, the fines, and spread into the farmlands and use it for enhanced rock weathering? So looking at this advantage, India has a humid climate with vast land availability, and optimal conditions for storage of carbon dioxide through removal by using interestingly, there are a lot of efforts in this direction where it is proven that it is beneficial and roughly 1 to 4 tons of CO2 can be captured per hectare annually, and India has roughly 150 million hectares. We have done some efforts in this direction. You can see the rock weathering intensity map for one district in Maharashtra, and we have sprayed these, and then samples are getting collected, and we are doing the analysis thoroughly. The final thing is I'm glad to share that with relentless efforts of the groups in India, that the government of India announced a $2.4 billion of commitment for doing CCUS in the country in this year itself, the budget that was announced in February. And that's a great push that India is moving ahead with decarbonization. And this is a segue to our efforts in CDR, because once we start uprising the subsurface, it can go ahead with that. At the same time, I represent the government at the IPCC as an expert on CCUS and CDR. At the same time, I head the delegation from the Bureau of Indian Standards. So we are building standards for the country for doing these things. Finally, we also wrote this CCUS handbook for policymakers supported by US DOE and CLGP, Department of Commerce. So we did a perception study, and there is a significant change in the perception of the country's mindset towards CCUS and CDR. Finally, we look forward to collaborative efforts, international and industrial engagements, and CDR in India should be linked with the just transitions because it needs to provide social license and regional equity. Thank you so much for the opportunity again and for the patient listening. Thank you.
Thank you so much, Vikram. Fantastic. We will transition over now to Kenya. And the next speaker is Lydia Olaka. She is a professor in geosciences at the Technical University of Kenya. Her research explores the East African rift system, including basalt formations, and the opportunity to pair geothermal energy with carbon mineralization pathways. Lydia, I'll turn it over to you.
Thank you, Jen.
I think we still need to put it on the slideshow mode.
Yeah. Yeah. Okay, yeah. Thank you, Jen, for the invitation, and thank you, audience, for being here. So, as you've heard, my name is Lydia Olaka. I'm based at the Technical University of Kenya, and I'm going to talk to you about the set of carbon capture and storage in the East African Rift, with a focus on Kenya and a few other places within Africa. So this is just to start off with a graph showing that there's a rising emissions within Africa, as you can see from various sectors. And this is important because some of the point sources are important for carbon capture and sequestration. We need to know where the sources are so that then we can be able to have proper ways of transport and also of storing. And as you can see, this from in the last 30 or so years, these numbers are rising. So I start off with really showing you the potential sites that we have within Africa. And as you can see, Kenya is here with a star, but it's also the area where we have the East African Rift, which extends all the way from the Afar in Ethiopia, going down into Tanzania and extending some places into the Mozambique. So in these areas, we have basaltic formations, which are important and what we have looked at for the sake of carbon sequestration. We also have some other areas within Southern Africa which have older basalt formations, and these ones have been tested in the lab and have been seen to be very reactive. So I think what we know now is that there are a couple of areas in Kenya. It is a bit advanced whereby we have carbon capture projects. We also have in situ mineralization going on. I think you'll hear later on from Sela. And then the enhanced rock weathering in various parts of Kenya, which is also led by FLAX and many other companies. In South Africa, there's a little bit of there are works which are being done by the Geoscience Council of South Africa. looking at basalt and in situ mineralization, and also enhanced rock weathering using the mine wastes that they have there. I think I also saw that there's Zambia and Tanzania. And Tanzania is just south of Kenya, whereby the enhanced rock weathering is ongoing. So it is important to show this because across the region, many of the companies that are setting up are actually borrowing technologies from each other. Or you'll find a company which is based in Kenya and is also in 2 other countries. And so it is important to sort of mention this because the knowledge gained in one area can be applied in other areas, especially when we look at the East African Rift. Okay, so why the East African Rift? The beauty of the East African Rift is that we have a lot of the volcanics, as I've mentioned, and you'll see here, which are in orange. And then there's also abundant faults. So these are structures which can be good or bad once we are able to determine how they are influencing the formations, because you need the faults or the permeability to be able to have water and fluid flow to the subsurface. And it can also be, it's important to note where they are because they can also be reactivated. So as a geologist, we need to know the role that the faults are actually providing at any one site. The other thing is that we have abundant volcanoes, the basalts and also many other volcanoes and high heat within the whole region. Further, the geothermal gradient is very high. So at about 700 700 meters, you could be already at 300 degrees. So this is also important because for carbon sequestration, the temperature is important so that you can be able to mineralize. Otherwise, it can then convert again to gas. So it's important to be able to map such kind of areas. And then the rift is also an area where there is tectonism, meaning that it is also moving, but very small speeds, like 2 millimeters per year. It's an extension zone. So we are also having some tectonic activity which need to be closely monitored. We have a range of basalts from mostly young ones, 40 million years old, and these are also, they tend to be very reactive, which is quite good. For the CCS, there's a lot of water abundant in the area, and also within the lakes, there's groundwater and lakes. And this is important for the CCS, whereby for the injection where you mix water with the CO2 into the subsurface. We've also looked at, there's a lot of experience already from geothermal, Kenya being a leader in the geothermal sector in Africa and around number 8 in the world. They have been able to drill deep wells up to 3,200 meters and above, and over 300 of such kind of wells. So the experience with having deep wells and managing them is already there, the technical experience in the geology. And and the energy mix is majorly a geothermal, I think up to about 45%. And the rest is from solar and wind. And as a result of that, then we have a good renewable energy mix. So what we have been doing is trying to look at how can our studies be able to support both in situ and ex situ mineralization. And within the in situ mineralization, whereby we have water mixed with CO2 and injecting this mixture into the basaltic rock, or also having supercritical or liquid CO2 and injected into the basalts where you have a caprock, and then this is able to carbonate. So our task is to understand how the subsurface is like, how the basalts are, what are their properties or their characteristics, so that we can be able to inform on what kind of method to be able to take. The other thing that we have also worked on is to advise on enhanced rock weathering. From the map, you see here on the right-hand side, Kenya is mostly, there's quite a large area that is degraded. As you can see, almost half of the area is mapped as degraded. Some of them are very severe. And this degradation also impacts on the soil fertility. So it's mostly erosion and the soil fertility. So it is important then to be able to find natural solutions or by using the enhanced rock because of the high volume of basalts that is in the area. These are basically crushed at different levels. So far, the companies that are working here are using mine wastes, and then these are crushed and transported to various farms. These have been used on farms such as maize farms and also sugarcane farms, whereby the basalt rocks are spread over and they have seen quite good growth with the dust. And also because the volcanic rocks also have trace metals that are important for the plant growth. These are just some photos from the within Kenya, which you can also see how reactive the basalts are. As you can see, this is a basalt rock exposure, and over it, this is on the surface, you can see the crust of carbonate which has been formed on the surface. So the reaction, is very viable, and because we are within the equator and it's also very humid and the temperatures are high, so the reaction of the basalts is quite high, and as you can be able to see that. So what our work is majorly focused on for now is that we want to be able to map the structures, how they are oriented, and also how much fluids they can be able to take. And this is really important when it comes to the reaction rates, how much quantities of CO2 can be sequestered, but also it is important for monitoring the way the reaction pathway and also the time which the carbonization takes. So we started this work a while back, around 2018 or so, but our first paper was published in 2021, where we are and this was basically a question if the East African basalts can sequester CO2. And what we did then was to look at to estimate the volumes of the basalts within the East African Rift all the way from the north to the south. And then we looked at some of the key parameters that are required for injection. So the availability of water, the subsurface temperatures, the permeability and porosity of the target formations, and then also proximity to the geothermal systems as a provision for energy and also for the heat. So by doing that, this is the map of what we looked at in various areas, whereby we identify 17 basalt formations within the rift. These are mostly the ones that are occurring on the surface. And from this, we recommended that the most suitable, using what we had then, was the Central Kenya Rift, and then followed by the Northern Kenya Rift, and then followed by the Southern Kenya Rift. And and I think many of so far, the companies which have been set up in the country have actually set up in the Central Kenya Rift, that area. So the studies we are conducting, we have still ongoing studies mapping the rocks, how they are. We are looking at the flow textures, we are looking at the porosity and permeability relationships, but also trying to understand how much the rocks can be able, their lab experiments to be able to check how much fluids the basalts can be able to take, the different basalts that we have within the rift. And then the other thing, which is an application for enhanced rock weathering process, we wanted to develop a method in which we can be able to monitor the farms where basalts have been spread on, to be able to see if we can be able to identify some carbonate and how it progresses. So that is one of the studies that is ongoing. And the other one is just looking at the characteristics in the subsurface. And so we've had geological mapping. We've also had geophysics, magnetism, and electromagnetism, and also resistivity in various areas, to be able to map the top 2,000 kilometers, 2,000 meters. So the top 2 kilometers, we want to understand how many formations of basalts we have, and what are their characteristics. And with the geochemistry, we're also looking at what is the percentage of the different minerals, the divalent elements like the calcium and magnesium within the different rocks. With this, we are also cognizant of the potential limiting factors, and especially on the technical side, and environmental and economic. So our work is really to try to be able to answer some of the questions that we are getting even from the policymakers. From the technical side, basically, also as much as the rift is active, there's also, and we have the faults. What is the potential of leakage of the CO2 that has already been sequestered? And also the induced seismicity. Some of these activities can be able to induce seismicity. And what is the impact of CO2 and other gaseous impurities like the sulfides and nitrous oxides that we also have, which are coming from the mantle. On the environmental side, you find that where we have the geothermal production are also national parks. So it's really trying to understand what will be the role or the impact of CCS on these national parks. And the other thing is that the same area, because Kenya is semi-arid, we rely on groundwater quite a bit. So what is the impact of sequestration on groundwater, the residents, and all the other fresh water? But of course, there's economic side is basically just the high capital investments, but it's to be able to know how much is required, and also to mitigate the risks. Then it is important to understand the risks so that we can inform those who would like to start the companies here. In terms of skills, there are lots of skills which are required for now. What we are doing is collaborations with the various universities, and also various companies that are already in the field. And then also we are thinking about developing some new courses so that the students are able to understand and also develop a pathway in the carbon sequestration or the CCS field. So there are skills in the art sciences, agricultural sciences, engineering, economics, environmental sciences, and policy science, says that we've been discussing how we can be able to help to bridge the gap. This work we've done with a few partners who are listed here, and that is my email, and that is part of my team when they were in the field. So thank you very much.
Excellent.
I'm open to questions and also for collaborations.
Thank you so much, Lydia. We will save our questions for the end of the panel, but I just want to say there's a lot of questions. So those of you that have spoken already, take a look and feel free to start answering some of those questions in the Q&A function. We won't be able to get to all of them at the end of the panel. But the next speaker I will introduce is Bilha Narangu. She is the CEO of Great Carbon Valley. Her work focuses on workforce and ecosystem development. helping build the technical capacity and institutional foundations needed to support carbon removal deployment across Africa. Bilha, I'll hand it off to you.
Thanks, Jen. My apologies, I'm not able to come on video because I am stuck in traffic, but I'll still take on the call. This is Nairobi. I'm calling from Nairobi, so those of you who know Nairobi is famous for its traffic. I was supposed to be home an hour ago. But really good to connect with all of you, and I'm hoping I'll be able to put on my video once I'm settled. But very excited to have this forum going, and just really good to hear what's going on in other parts of the global south. And happy to speak about some of the work we're doing in Kenya. And I think it's a good segue to what Lydia just, Professor Laka just spoke about in terms of the sequestration efforts that are going on in the country, and the East African Rift for that matter. So as Jen mentioned, I am the CEO of a company called Great Carbon Valley, and also a co-founder of a nonprofit called Jacob's Ladder Africa. With Great Carbon Valley, what we're trying to do, as the name suggests, is essentially look at the Rift Valley, and it's kind of a play on words, and say, is it possible to use the Rift Valley as a carbon sequestration destination? And again, leading up to some of the work that Professor Laka was talking about. And what we're doing with that particular, what we're doing in that particular company with Great Carbon Valley is we are looking to develop direct air capture and storage sites. And so what that means is that we'll find suitable sites, and suitability here means basalt formations that we can store carbon in, and then pair that with ideally geothermal energy because of the waste heat and just the baseload power, and other software amenities that are required. And the idea and the hope is that we can make East Africa a global hub for carbon capture and storage. And then with Jacob's Ladder Africa, we are a workforce development nonprofit and focused on the green economy. And again, our thesis here is we believe that the green economy will be a significant job creator in the coming years. And on the flip side, we have a growing workforce population. As most of you would know, Africa is the youngest continent. Our mean age is about 19.9 years, and that's actually getting lower. So we are essentially going to be the workforce of the future, which therefore means that, but the thing is we need to create jobs for these young people, at least prepare these young people for the jobs that ideally would be coming. And so our thesis here is that if we believe that the green economy is going to be a big deal, then how do we make sure that our young people are ready for it? And so narrowing it down to the purposes of today's conversation, within the green economy, one of the upcoming industries that we've looked at is the carbon removal industry. And again, it's very nascent and very, very new, not just in Kenya, but globally, just listening to the different conversations that have been had so far. A lot of countries are just beginning to look at what they can do with carbon sequestration and storage, or just carbon removal in general. Just so you know, Kenya is potentially the highest or the second highest issue of carbon credits on the continent, depending on which year and the methodology that's counting. But in most cases, a lot of these projects tend to be nature-based type projects. So that's what people have been used to. And so part of our work has been to sort of sensitize and just get people used to the idea that this can be and should be a destination for high quality carbon dioxide removal projects. And so that's what we're looking at, things like direct air capture, biochar, enhanced rock weathering, etc. And so again, for us becomes an important way to sort of say, nature-based solutions are great and we'll continue to do them, but technology-based solutions are actually a very good way to create jobs that didn't exist before and begin to literally help us industrialize. Because one, it's in that most of these are industrial projects where, and they require energy, they require a workforce that will, a technical workforce to go with it. And so we are literally at the ground zero of this particular industry, but we think it's actually a really good time to begin to think through some of these questions and some of them that Professor Laka began to talk about. And a couple of things I think that are important to note is CDR in general, and especially tech-based CDR, is nascent globally. So there's no real, there's no geography that can really claim expertise or not expertise is there, but what I mean is a long history of doing these things, or, places where we can say that CDR efforts have been going on for years on end, and so those markets have matured. So in some instance, one could look at any geography that's starting to look at CDR, and especially engineered CDR, has a unique advantage because we are all starting from ground zero in a sense. And what that means is that we are looking at everything from the policy requirements, from some of the questions that are being raised around what are the environmental considerations, things around energy, and now in particular for me, what workforce is required. And what we are now finding is, one, because it's a very, very new industry, people don't know much about it, and that's everyone. When you talk to a lot of universities, policymakers, and the students themselves, like even just getting people to understand what CDR is and what engineered CDR is in and of itself a very, very new task, and something that we're having to spend a lot of time doing. So to that end, one of the things that we ended up doing was we created or came up with what we call the Carbon Removal Alliance in Kenya. And this is an association of different companies that are doing CDR, working on CDR. And part of our recognition was that we needed to have a unifying body that is speaking about CDR. What is CDR? What are the benefits of CDR? And what will Kenya and the East African region need to do if we are going to become global leaders in carbon removal? So I think just one point to land home is just the fact that this is a very nascent industry, and so there's a lot of education or just awareness that is required across board, both policymakers, academia, and the labor force itself. So just getting people to understand that there's something called carbon dioxide removal. It's a potentially really big industry, and there's going to be all sorts of specialized roles that are required. So that's one thing. So the first thing is awareness. And the next thing that we started to work on significantly is curriculum development. Again, this is very early. And as most of you who are in academia would know, a lot of times it takes a while to move curricular development and getting people to change curricula or introduce new curricula, as it were. So to that end, what we're having to do is, in addition to creating awareness, we're sort of saying, okay, what courses or what existing courses are very closely aligned to CDR. So it's looking at things like geology or things like different engineering courses that will be required for this sort of industry, and sort of saying, can we target graduating students from those courses and see what does it take to get them to know more about CDR? So whether it's the awareness bit, whether it's taking some short courses, whether it's providing just some introductory courses around this is what CDR is, and here's how you can skew what you already know to become aligned with the CDR industry. So again, there's a whole bit around curricular development, but I think what we need to do is, in addition to working with universities to have longer term training courses, there's quite a bit of work that needs to be done around, or that can be done around, providing introductory materials and just getting people aware around CDR, and seeing how do we partner with people that are already doing CDR training, and saying, can we get some of your courses and do some short-term courses, especially when the universities are closed. We've done some of those things with some of our partners like Kune Foundation, etc., where we actually, they organize short courses, and we have students come in for a week or two and give them this sort of short introductory, but, fairly packed courses on CDR. Then the last bit is, for me, thinking about, so there's a more technical workforce development that is required. So here we're thinking about your engineers, your geologists, etc. But then it's thinking about, when we think about this as an industry as a whole, we have to be cognizant of the fact that you need a whole ecosystem of people that understand the industry. And that's everyone from financiers, like how do we get people that understand how financing in the CDR market works. We get lots of questions around just how do carbon markets work. A lot of times when I present some of the work that we do, people are surprised to think that a whole company can be built around just selling carbon credits. And usually they would be sort of like, okay, so what do you do with the, what do you do with the carbon? We saw it underground. Then what happens? And it's usually a very, you can tell it's a lot of light bulb moments for a lot of people, just because this whole essence of carbon dioxide removal, carbon credits, all that stuff is very, very, actually for a lot of people, it just doesn't, it's very, very new, or just they're not familiar with it. So there's quite a bit of work to be done around just thinking through what's the ecosystem required to just making sure that people understand this, and whether it's the policymakers, whether it's, as I said, the financiers, or just other people that would be working. They may not necessarily be working directly in the CDR industry, but they would be supporting CDR companies. So you'd want them to be as much as possible aware of just the carbon markets and CDR in general. So again, quite a bit of work that we're having to do with that. And some of this incorporates short courses as we talk about, or just awareness building campaigns, and now working with partners to sort of say, okay, what would it take to get a group of executives aware of CDR? What would it take to get a group of, policymakers, trained on some of these things? But yeah, I think I'll pause there, just looking at the time, but the overall, for me, the overall takeaway message is this is a growing industry, despite all the different hiccups that we've seen. And if we can get people, especially in some of these global South markets, aware of the industry, and especially young people, and begin to get them to think of this as a career they can get into, it becomes an interesting way to make sure that we are solving for the skills problem, so that, as if you're having companies and attracting companies to come to Kenya and to come to some of these places to set up, they're not asking, will you get the engineers that we need? Will you get the people that we need? That should be a solvable problem. And for me, it also becomes a way to ensure that we are creating jobs in a fairly new industry that hopefully, will continue growing and create more jobs for our young people. Again, I'll pause there. I'm happy to answer any questions, but we'll hand it over back to Jen. Thank you so much for the opportunity.
Thank you, Bilha. And you're amazing in Nairobi traffic and still made it to your talk on time. So amazing. Thank you. Drive safe. And we hope that you are through the traffic soon. And now we will transition into Q&A. And again, we don't have a whole lot of time, but I want to introduce my PhD student, Likwa, who will moderate the Q&A here. And I think we only have time for a couple of questions. A little background on Likwa. Likwa is from Zimbabwe, has his bachelor's and master's degrees in geological sciences, and then very bravely joined our team to get his PhD in chemical engineering. And to me, it's really a combination of a perfect skill set. When we look at carbon dioxide removal and scaling up, it's really critical that we leverage a lot of the nature-based approaches that we heard about from both Vikram and Lydia and also in Brazil, enhanced rock weathering, and also approaches like biochar. And my guess is that if we are to really truly have durable carbon removals in this space, we need to be able to develop the monitoring, reporting, and verification. I think behind that is a lot of engineering. And so bringing together geosciences and engineering, chemical engineering in particular, super excited to introduce Likwa. His PhD work is on that. But Likwa, I will hand it off to you to maybe pick a couple of the questions in the chat that gives the panel that's here a chance to answer.
Definitely. I think we'll just stick to two questions really because of time. And so the first question I'd like to ask is, with regards to the utilization side, Brazil seems to be a key leader in terms of utilization for CO2. And I'm wondering, as a global leader, particularly given the sugarcane sector, what are some of the blockages or some of the bottlenecks that the industry is experiencing? And yeah, I guess let's start there with some of the blockages that are present for the scaling of the CCUS industry in Brazil.
I guess that the two first questions are for me. Okay, about the first question, what's blocking scale deployment of the CCS activities, mainly CO2 geological storage, in my point of view, is, for example, the lack as regulations in Brazil to CO2 injections. So in Brazil, at this moment, we have no regulations in the states to CO2 injections in geological reservoirs. That is a problem, okay? Another problem is in economic point of view, because we need to do the CO2 geological storage projects should be economic feasibility of the project is a problem. We need making project economically viable. This is a big another problem, because in the technical point of view, we have several projects to select the best areas, to characterize geological reservoirs, to modeling how to inject CO2. So I guess that the first problem is lack of regulation. Second, funding for pilot projects. And the last one, time, because our project is to select the best areas, geological reserves, and so on. Start at 5 or 6 years ago. We started to define the situations, but in few years we will have all the projects to start pilot project to inject CO2 for BECCS.
Thank
And
you.
sorry?
Oh, sorry. I was just thanking you for your answer, Professor Tassinari.
Okay.
I appreciate the note in terms of the regulation needing is something to catapult the industry further. I just wanted to ask just a summarizing question, particularly for time, if respondents please keep their responses short. I think it was Professor Lydia Olaka that had said that the knowledge gained in one area can be utilized in another area. And I think that's just a good question to ask all the different regions, looking at Brazil, Kenya, and India, each with major representative opportunities for CDR. To close, what is one idea from another presentation today that excited you? And what is a unique strength that your region has that another region could learn from in terms of scaling CDR? And that's an open question. If you'd also like to start us off, Professor.
Just I have one second question about if in Brazil there are an important pilot or commercial projects.
Would it be possible to answer that in
We
the
have
chat?
now at this moment, and the project is for EOR, enhance the oil recovery to improve the oil recovery in the offshore basins. And I have another one in onshore basin, is ready to start up, but has not yet begun. Likely due to regulatory issues and another problem. I don't know why, but that's all we have now at this moment to produce injections of CO2.
Definitely. Thank you so much. I was wondering if any of the other presenters had any summarizing thoughts, just to offer one unique idea from your presentation, a strength that your region has, and what other regions could learn from that strength in terms of scaling CDR.
Maybe I'll just chip in here. Of course, India is a huge landmass, so we are moving very in a very progressive way with biochar. I did not mention a lot about it, but we have close to 100 startups in the space of biochar, and that are getting accelerated. A lot of biomass burning happens. So instead of that, can we create biochar and use it in the farmlands, which does serve the purpose both ways. And then that's the organic way of capturing, but we also have the inorganic way, which is enhanced rock weathering, which I did talk about. The time is the essence here, and that's where we feel that that the policies and the regulatory bodies and regulations and also the funding needs to accelerate in terms of if we want to see the words into action, particularly in the Indian context, and I'm sure other places as well are facing different sets of challenges. The second component is that at the IPCC, we decided to write the methodology report for CDR, essentially, and CCUS included, and that the scoping meeting that was held in the last plenary in Peru. And that outline was accepted by all the countries. And now this next 1.5 to 2 years, we expect that to be out. So as much as we publish good research and give the data from different countries, that becomes input to a very robust scoping methodology report. And that is also an important thing that we all can work together. Thank you.
Yeah,
thank you so much. Go for it.
Yeah, thank you. Maybe what I can add also, I think the strength that Kenya has is also in terms of the young population that Bilha mentioned about, who are also well trained. And they're very quick to learn. Like if you look at the company which have already been set and doing the CDR, these are people who they come from different engineering, like in mechanical or even chemical engineering and geology, and they were able to learn in a very short time period and are now running those companies. So I think the young population that is really ready to pivot and to take advantage of what is there is one of the strengths that we have. And then the other thing is that there's quite a lot of the basals, which we have on the surface, because we have quarrying activities that are having the wastes, the small fines, which can then be used for enhanced rock weathering. So that one is already available because there's a lot of construction in various areas that are using the rock. So those are the two that I can talk about in Kenya. Thank you.
Thank you so much, Professor Luck.
So I'll chime in here and just kind of related to the question around regulations, etc. So I think because part of our learnings has been because this is a very new it's a very new field. So it's very likely that most countries will not have necessary regulations for some of the work that we are talking about. But one of the things that we've noted that has worked fairly well in Kenya, and I guess could be taken in, is trying to identify similarities with existing industries and working with the regulators and saying it's almost like allow us to use existing regulations even as we are sort of building out and working, because part of our work with the Carbon Removal Alliance is really helping the government to help us regulate, like actually come up with the right regulations. And so I think there's two learnings here. One is this idea of, so for example, in Kenya, because we have a long history of geothermal, we've kind of used some of those regulations to, guide the work that we're doing in subsurface injections, where we're saying we're drilling, we can kind of use those regulations to get us started, but at the same time, being quite deliberate to work with the policymakers and saying we actually want to develop robust regulations to regulate the industry, because again we realize it's very hard for us to build a significant industry where people are not quite sure around the regulations around it, and you don't want people kind of saying we don't want to build an industry and then 2, 3, or 5 years later the government comes back and says no, this is not allowed. So I think there's also something about actively working with policymakers and helping them actually come up with the right regulations so that the industry is well regulated and people are quite clear on what's expected of them, even as they begin to make investments in this field. Thank you.
Thank you so much. I appreciate all the responses, and I think now that we have also some more activity in the Q&A, we can move some of the responses to there. So if you see questions that are directed towards you or that you think you can answer, please could you type an answer in the Q&A and provide your answers there. Thank you so much for all your presentations. It was really, really interesting. I'll hand it back to you, Jen. Thanks so much.
Thank you so much, Liqua. We will transition to session 2. And I want to introduce Hélène Calorge, who's in our group. Hélène has been working with me as a research associate for, I think, going on 7 years now. Amazing. Hélène has her PhD in geological sciences. So we have a few card-carrying geologists in my team at Penn in chemical engineering, again, trying to bridge the interdisciplinary. And Hélène's work is focusing a lot on mapping, co-location, and logistics. You can learn more if you look at the CDR Primer, which was a book that we published in 2021, and some of Hélène's amazing maps are in that resource. And with that, though, I'll let you take over the next session, Hélène.
Thank you, Jen, for the introduction. And I have to say, I was really excited about some maps that I saw in the first part of this webinar. So good morning, good afternoon, or good evening to everyone, depending on where you are in the world. This is the second part of this webinar. And now we have heard about several technologies to achieve durable CDR. We are going to switch gears to talk about deployment and commercialization pathways. So we know that multiple actors are always involved to successfully deploy a given CDR pathway, and also CDR pathways need to be integrated into existing systems. So this discussion is about partnership models for scaling BECCS and DACCS and practical insight from subsurface and energy sector expertise. I'm privileged to welcome a panel of 4 major organizations in the field who are currently deploying CDR at the commercial scale in Kenya, Brazil, and India. So for the audience, I remind you that please don't hesitate to submit your questions in the Q&A at the bottom of your screen. So the first organization that is going to speak to you is the Geological Survey of India. They work on national geological mapping and basalt characterization to support safe long-term CO2 storage. Our speaker is Dr. Bibas Sen. He does active research in volcanology and geochemistry of mafic lava provinces of India, like Deccan and Sylhet. Bibas, I will pass it over to you.
Yeah, thank you, Helen. First of all, let me thank Professor Wilcox for having me here. Let me share my presentation and we'll continue the discussion. Is it visible to you?
Yes, that's perfect. Thank you.
Yeah, thank you. So thanks for this opportunity. And as the topic is like that, we are going to talk about the national geological mapping and the basalt characterization to support safe long-term CO2 storage. We have a huge relevance of CCS, or rather CCUS, in achieving net zero target, with India trying to achieve net zero in 2070. And with increasing per capita emission every year, India is now 4th largest emitter in the world. And one of the studies by International Energy Agency way back in 2010 says that CCS is expected to mitigate 1/5 of the emissions that is coming up by 2050. So this gives a background that CCS is one of the new technologies that needs to be implemented when we are looking into achieving net zero targets. This is well known. My previous speakers from Kenya and other parts of the world have said about this one. What we are trying to do is breaking the silicate bonds of basaltic rocks, making safe carbonates, and this has been aptly demonstrated by Walula projects of in Columbia River basalts and commercially viable Carfix in Iceland, where tons and tons of CO2 is being injected per year in the Icelandic basalt. Now, looking into in our backyard in India, we have a huge area of huge surface area covered by basalt, which is known as Deccan basalt. About 500,000 square kilometer of on-land Deccan basalt is there, and the importance of this particular basalt is that they are near the industrial regions like the Mumbai-Pune region, if you can see my cursor, or the Gujarat regions, which are the industrial hub of the country as of now. And also, many of the nearby industrial areas have some basalt or the other exposures related to Deccan. And Professor Vishal and his team have estimated the sequestration potential of about 94 to 305 gigaton of CO2. So with this backdrop, Deccan basalt has been a center of studies for CCS research for last 5 years or so in India. And if you see into this, DEM, digital elevation model, the basalt are like exposed on surface along a escarpment, which is shown towards your left, where you can see layers of lava flows. And our job as a geologist was to map those lava flows and to see how they can help in our understanding. In fact, this lava flow mapping started way back when we started looking into each and every lava flow. We saw that the lava flows have tripart structure with some vesicular or brecciated crust, and then a dense core, and then another vesicular base with or without interflow horizon, sometimes red in color. They are basically clay rich horizons which act as an aquitard in terms of the percolation of water or fluid, so to say. And these basalt come in different structures. They have different fracture sets, and they respond to different kinds of mineral carbonation reaction, which I am going to show later part of this talk. As far as their composition is concerned, they as like any basalt, they also have lot of variations as far as their composition is concerned. Sometimes plagioclase, which is one of the components, which is calcium rich part of the silicate mineralogy, and sometimes we have magnesium rich basalt. Now, if you see the lower two plots, you see quite a range of composition from picrobasalt to basaltic andesite, which gives you an idea that lava flows are not kind of having a same composition, even though we call them basalt per se. We started, as I said, we started mapping maybe 30 years back, when the recent analytical facilities were not that very much common, especially in countries like India, but now they are very common. We started looking into the lava flows based on their hand specimen character and building up the different lithosections and coming out of maps, particularly in 1:50,000 scale. And these maps are available in public domain. So any person in India or world, they have to just make a simple registration and see these maps. And later on, as I said, with time, these maps were compiled from 50,000 to two different scales. And you can see this map, which was basically green color monochromatic, has now many formations and beautiful disposal of different lava flow, disposition of different lava flows. The later studies also carried out by other institutes in India have given a fairly good thickness of basalt, around about 2 kilometers, especially towards the northern part, here, somewhere here, and to the western part of the basalt, making them suitable storage sites of in situ injections. And the lithostratigraphy, what we built earlier, is now validated through chemostratigraphic studies, chemical analysis, and the stratigraphy more or less matches. There is hardly any discrepancies as far as the litho and chemical stratigraphy, though the names are different, but the the lava flow package behave basically in the same way. With this backdrop, we wanted to look into how the surface lava flows are behaving as far as mineral carbonation reaction is considered. And from we started looking into around 1 lakh square kilometer and we collected some 200 bulk rock samples, and from there we concentrated our study in the lower part of the lava pile, the lower part, which I don't want to name each and every formation for you, but it is from the lower part, and we plotted them and started our mineral carbonation reaction in collaboration with IIT Bombay Professor Vishal Vikram's group, and picked up 3 composition, one from picrobasalt, one from sensitive tholeiitic basalt, and one from basaltic andesite, and subjected to them in different pressure temperature conditions, and we really have got magnesites in picrobasalts or clay in basaltic andesites with experiments varying in temperature from 100 to 140 degrees centigrade and pressure 50 bar times 1, 2, 4, 8, and 12 weeks. So these results have come up sometimes in December last year, in which we can identify those lava flows in which a particular rock composition has given significant potential for mineral carbonation, and those composition, those lava flows have either picrobasalt or basaltic tholeite as far as the composition is concerned. Now we are still into the phase 1 of the research, and we are looking into the other lava flows having a different type of a composition, like giant plagioclase basalt, or the different parts of the particular lava flow, lava crust, or the bowl beds or interflow horizons, the red colored clay horizons, clay rich horizons that I have showed you. And we are also trying to understand how the effects of clay and alteration products are affecting the mineral carbonation, because this lava pile is a 66 million years old, and our drill hole data, we have 8 to 10 drill hole data on the Deccan basalt. This drill hole data suggests that there has been substantial amount of alteration. So what are the role of those alteration products as far as mineral carbonation, especially in situ mineral carbonation is concerned, and the release of heavy material, if any, through this mineral carbonation? If we are using this basalt for enhanced rock weathering, will it harm the crop, the human health, so to say? This aspect is also being taken care of. And with this, we are progressing into the second phase, in which we are trying to understand the mineral potential of subsurface lava flows. As I have said, that there are about 1.5 to 2 kilometer thick Deccan basalt is available, and western part of the Deccan is suitable, as they have a source of CO2 in the Mumbai-Pune industrial area. So we want to know how this lava flows will behave as far as their composition, mineralogy, geochemistry is concerned, and they will generate some data for injection simulation study. So whether we use a CO2 plus H2O model, or we use the supercritical liquid model, the need of the hour is to look into to do some actual pilot injection, and we are hopeful to begin with small injection test in collaboration with IIT Bombay, and to prove that it is, Deccan basalt can be a very globally significant and viable site for CO2 sequestration through mineral carbonation. Thank you. This is my email ID. Thank you for your patient hearing.
Thank you, Bivas, for this great presentation. Now we have Octavia Carbon, the deploy solid sorbent direct air capture coupled to geothermal energy in Kenya. Our speaker is Sifa Kinoti, and she's the head of policy and partnership at Octavia Carbon and focusing on aligning innovation with national climate strategies and positioning the global south in the future of durable carbon removal. Sifa, I pass it over to you.
Thank you. Thank you so much for the time. Thank you so much for the wonderful introduction as well. I'm super happy to be part of this conversation. So I started out with the email in case anyone would like to reach out. And what I'm going to do in this presentation is just three things. Tell you a little bit about Octavia, why we chose to do it in Kenya, and the lessons that we have learned from scaling our technology from the lab to the pilot. And those lessons are threefold in terms of the technology, the governance, and the financing. So a little bit about Octavia Carbon. We're the first direct air capture facility in Africa. We're based in Kenya along the Rift Valley. We're co-located with Salam Mineral Storage and also a geothermal energy provider, as you've heard from the different presenters who've come before us, or rather who've come before me. So our pilot plant along the Rift Valley has been in operation for close to a year and a half now. And it has a capacity of, or rather it's been designed to have the capacity of 1,500 tons of CO2 removal per year in the next 10 years. And of course, we scale it up in phases. So right now we're close to about 60 tons a year removal capacity. And the beauty about this technology is that it's all designed, patented, and manufactured in Kenya by the different, by Kenyans, by the different engineering fields that has been alluded to in the different presentations. And we've been able to provide over 100 skilled jobs in the STEM field. I'm not going to go much into depth about why Kenya because it's been covered previously pretty well, but just in three steps, or rather in three major points, we have the geothermal, we have the talent, and we have the geological storage potential. So now I'm going to get into what we have learned in terms of, the three things that I had mentioned earlier, first starting with technology and the lessons that have that are going to affect you if you want to start a direct air capture plant anywhere in terms of tech. So the first one is energy integration. We're all aware that DACC is a very intense process to do, and it needs energy in terms of heat and in terms of electricity. So the heat is the most the heat capacity is the one that is actually much more than the electricity capacity that is needed. So that's why it fits very well with the geothermal baseload in the Rift Valley where we're located. And number two, for you to also run your operations, you need to be low cost, and it also needs to have a low carbon source of energy. Otherwise, you're just doing a zero-sum game, emitting CO2 to capture CO2. So you need to have a low cost and reliable clean energy power. And that's one of the biggest lessons that we've learned in terms of energy integration. Second one is in terms of industrialization and manufacturing. It's important to build local fabrication skills and supply chains for the materials and the components that you're going to use to build the machines and to deploy the machines. Something that we've done to build the talent and also to build the infrastructure is that we have memorandum of understanding, excuse me, with different technical vocational education training centers within our region of deployment, where we go and we train the students, and then eventually they become the talent base that comes to work in the field, in the operations at the Rift Valley. We also have strong partnerships with the different universities that we were able to form that talent pipeline that's able to contribute. In terms of local fabrication, it's important to ensure technology transfer and partnerships with other manufacturing firms within the country so that you're able to really build faster and at a lower cost. So the third is just generally looking at infrastructure. When you're setting up a direct air capture facility, you need to think about the supporting infrastructure for capturing the CO2, for storing it, for conditioning it, etc. So the first one is kind of interlinked with the energy integration point that I mentioned earlier, and this is heat integration. So as I mentioned, DACC is very energy intense, and a lot of that energy that is needed is thermal energy, and that makes it a good use for geothermal energy. So you'll need to figure out, especially if you're co-located with the power source, how to integrate it. And it becomes very challenging. It's not something that is widely done. So this is a new technology or a new type of infrastructure that you'd have to build out. You'd have to research the effect of, for example, hydrogen sulfides and other chemicals that are found in the geothermal steam and how it's going to affect your DACC processes. You need to think about the different temperatures. You need to think about what to do with the waste, brine, etc. Yeah, you get the picture. The second one is in terms of CO2 transport, especially if you're transporting to a storage provider. Right now, at the scale that we're at, because it's still at the piloting phase, you can still transport it via truck, where you do a couple tons per trip. However, if you're going to scale it and get it to the megaton scale, you're going to have to think about pipeline integration between capture sites and storage sites. So that's one of the active conversations that's being held. And how would that look like? How to finance that? Again, how to design your plant so that it can integrate with the different with the pipeline transportation, in terms of pressures, in terms of the purities, etc. And lastly, you also need to collocate next to the storage infrastructure. As mentioned by the previous presenters, we are collocated next to geological storage, and that makes it much easier for us to transport, and it also lowers your embodied emissions. The second factor that is very important to deploying and to scaling is regulatory alignment. So again, dividing it into three. One is environmental integrity. Number two is your social license to operate. And number three is the policy alignment. Number one, in terms of environmental integrity, it's been said by the previous presenters that there's no regulations for DACC because it's still an upcoming industry, it's still a nascent industry. So you would need to show to the authorities and also to buyers that you are maintaining the highest levels of environmental integrity and not causing any more harm to the environment by the deployment of your solution. So a lot of times when it comes to DACC, you mostly want to pay attention to your energy use. One, where you're sourcing your energy. Number two, how much energy you're using. Second is your water resource management. As I mentioned earlier, a lot of the energy that's needed is steam, that's water. So how you're going to use that water within your DACC system, how you handle the wastewater is very important. And number three is monitoring of your life cycle emissions. Life cycle emissions are just basically the amount of CO2 that you emit in the process of capturing CO2. So you have the infrastructure that you're building, the steel, the concrete. You also have the energy source that you're using to power your machines. You need to factor in those emissions, and you need to be aligned with the global standards, best case standards for carbon projects and for climate projects, and ensure that you're aligned with those standards when you're deploying your solution. Number two, which is very important, is a social license to operate. So this means wherever you're going to set up, you need to do a lot of community engagement and get their consent to set up the project, and also make sure that you're providing benefits to the local community by you being there. This could be in terms of employment and other benefit sharing mechanisms that they would suggest. So the other thing is to make sure that whatever the community says, for example, if they say that the biggest issue is in terms of water or in terms of energy, for example, you would need to work hand in hand to support the solutions that they come up with. And one of the things that we've done here, as I mentioned earlier, is the partnerships we have with the local TVET institutions to provide that local employment. And number three, have to make sure you're aligned with policy. So you have to make sure that you're aligned with the national climate strategies, the energy strategies, the industrial plans. That way it's just easier, especially for government officials to really prioritize and to understand what you're doing and how it aligns with the national goals. And then they would be able to give you a space to create the regulatory and the licensing pathways that are needed to scale this industry. So the last and one of the very most important factors that we have learned in deploying and scaling this technology is financing. Direct air capture, this kind of technology has high upfront capital because it's a first of a kind tech. There's a lot of R&D that's needed into it. And unfortunately, there's limited financing for hardware, and there's also long development timelines. As I mentioned, you're not only developing DAC alone, you would have to work with or rather energy providers, storage providers, transport. So all of that supporting infrastructure, building a manufacturing capacity in Africa or in the region, it has long development timelines, so it would need a lot of patient capital and a lot of upfront capital for that. Number two, there's a challenge of the market. Primarily, the main source of revenue comes from the sale of carbon credits, carbon removal credits in particular, which I want to assume that everybody in the audience is aware of. Right now, the cost of direct air capture credits specifically is higher than the other types of credits that you can buy in the market, which limits the kind of buyers that would be able to purchase your product, which leads to kind of like the third gap that I want to mention on financing, which is a chicken and egg situation, because a lot of times for you to fundraise a capital to build your technology, they would want to, or rather the financing institutions would want a guarantee that you have a buyer, but you need the buyer so that you can get the financing. So it's usually a merry-go-round, and it's one of the biggest challenges when it comes to deployment of these kinds of technologies. So I will leave it at that. And I'm open to taking more questions at the end of this panel. But as a parting shot, just wanted to share the three main things that we've learned in deploying our technology in terms of aligning yourselves with regulations and governance, in terms of fundraising, and also in terms of technology deployment. Thank you.
Thank you, Sifa. It was an absolutely great roadmap for how to deploy CDR. So now we will transition to our next company. We have Svante, and our speaker is Taylor Huff. He's the head of carbon markets for Svante. And this company deploys carbon capture technologies, enabling BECCS and integrate with direct air capture systems. They foster partnership opportunities for global South deployments. Taylor, I will pass it over to you.
Yeah, thanks, Elena. I'm grateful to be here. Let me share my screen.
We're seeing the screen with your notes.
Okay, let's see here.
So if you go to slideshow at the top, you should be able.
I'm on a Mac, unfortunately. This is why the dry run was important, huh?
Alternatively,
see
you can
here.
go to the little square at the bottom of your slides too. There's like a little.
Yeah, that one.
There you go. That'll do it.
Is it showing my notes again though?
Yes.
Okay.
Otherwise, you can just
when you press the slideshow, there's a button at the top where you can swap displays.
we can see still your notes, but like you can
at the top you can see where you can swap displays.
Taylor, there's a swap displays button
at the top of the Zoom app or within PowerPoint?
At the
PowerPoint, I think. If you go back to your slideshow again.
Okay.
Or maybe you can do it.
Oh, up here in the slideshow rhythm or ribbon.
Back at the bottom where it has a little rectangle, if you press it again. Yep.
Okay.
Do that. And then look at the top. You see the swap? It says end show or swap displays.
Unfortunately, it takes over my screen when I do that, when I do this.
Oh.
Yeah. Well, maybe I just minimize the ribbon and sort of maximize within the window here.
Yeah, that works.
Okay. 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 Anyway, there we go. Yeah, so here today representing Svante, and I'll be talking about potential for BECCS in Brazil and India, more from a market and commercial perspective. And really the thing that I'm the most excited about and would be my main takeaway is that I think there are opportunities to build CDR projects at commercial scale in the global south today. And I think what's quite unique about and key advantages of the CDR market is the product is virtual, right? Carbon credits, it's not a physical commodity. So not needing infrastructure to be built to deliver product from suppliers to buyers, that's a key advantage here. And it also means that in countries that don't yet have a domestic carbon regime, or really there's not a economically viable path to very high carbon taxes. I mean, some of these regimes to actually enable CCS, need to be quite expensive. This is an unlock. Projects can be built, literally anywhere. The product, the carbon credit, can be provided to buyers. Doesn't require domestic carbon regime. And compared to other products and technologies in the energy transition, this is quite unique. Renewable electricity, hydrogen, green ammonia, methanol, biofuels, all these products need to connect physically, the buyer and the supplier. And the infrastructure and the distance needed to connect those can be quite prohibitive. So I think that really creates a good now opportunity. And then for background on Savante, we're a Canadian carbon capture company, been around for almost 20 years. And our core DNA was and really still is solid sorbents as an alternative means of either point source or direct air capture. And we've been through quite a journey of working with different types of sorbents, now working with metal organic frameworks. We've built 4 demonstration plants to test, scale up, and further optimize those solids. And also now a manufacturing facility in the Vancouver area. We supply much of the DAC industry with solid sorbent filters, and it can also be applied to point source as well. And so here for a bit of a visual on our technology, applied for point source, but in essence quite similar for DAC, albeit with different capacities. It's a solid state system. We apply the solid sorbents into filter beds, and then these filter beds are combined into cartridges, so to speak, and then into this spinning wheel, almost like a cheese wheel of little pie pieces. And how it works is point source or DAC flue gas is flowed through the sorbent beds. The CO2 selectively physically absorbs into the metal organic framework. And then as the wheel spins, there's a step where steam is introduced to regenerate the sorbent. Not that dissimilar to liquid amines. There's the heat addition step to release the CO2, and then a cooling step as the cycle returns back to the beginning. And the reason we've gone through all the effort to do this and not felt that liquid amines are the ideal long-term solution is from a cost perspective, yes, but also reducing the volatile air emissions of liquid amines. So a solid-based system doesn't have those volatile air emissions, and also has a simplicity that's easier to integrate into various emitter sources. It's more of a start-stop solid-state system instead of a small chemical plant that needs to reach certain steady states and has a very defined startup and shutdown procedure. And so at the moment, we we're not active in the global south, although we definitely would like to be, and would love to talk to various groups about partnering on project opportunities, mainly because proximity to home, quote unquote. We're more focused on North America to date, and also key, I think, as we all know, on proximity to onshore storage, typically saline aquifers in the case of North America at the moment, but that's really been the driver of where we find project opportunities that are viable. But taking that same approach elsewhere, we would definitely like to do that. And we structure our projects as joint ventures or joint projects with the emitter. So in the case of these three projects, they're all existing biogenic CO2 sources. Two are different types of pulp and paper mills, and one is a biomass power plant. So the idea is that we work together to co-fund and share the development responsibilities to take a project to FID and then into construction. And we're trying to do this at scales that are large enough to come down the cost curve and meet the needs of the CDR market and buyers, but not too large that it sort of swamps that market. So that's a delicate balance, because anything in this space, sequestration, mineralization, carbon capture, it really does look better at scale from a cost perspective. But as Sifa mentioned, it's a bit of a chicken and egg to get there. And we've actually, two of these projects will have dedicated greenfield TNS built via short distance pipelines. And we find, and I think this was not necessarily our first instinct, but we do find even at these scales that it can justify and be the anchor volume to build a storage hub that then could open itself to other emitters or future phases of projects. Our most advanced project is in Saskatchewan, with the picture shown here. And to just give a feel for the physicality of it, it's quite remote northern Saskatchewan. It's a partnership with the Meadow Lake Tribal Council, which is a band of First Nations, Indigenous nations, that they've built a quite elegant and integrated forestry products supply chain, where they harvest lumber from boreal forests in the area, and boreal forests by nature, by definition, regenerate themselves via wildfires. So they're focused on harvesting the forest in sort of a patchy manner to simulate the effect of a wildfire. And then they have an existing sawmill that produces lumber products, which goes into the housing market primarily. And then their latest addition has been to build a biomass power plant that also produces heat, a CHP, using the sawmill residues. And then our project will be the last leg of that to capture the CO2 and sequester it, which one could say it's sort of using all parts of the tree. So the tree is harvested, lumber products, and then energy production for export, heat going back to the sawmill to dry. Feedstock is needed, and then carbon capture on the back end. And we're working towards FID and start of construction early next year on that project, and then about a little over 2-year construction cycle, which that is that's also the reality and the challenge of our industry. Is these things take a couple of years to develop, they take a couple of years to build. Sometimes they take a couple of years to permit as well, or work through quite new regulatory regimes. And so then now switching to Brazil, here's a map of southern Brazil. And this map shows the Parana Basin, so sedimentary basin. We expect, although far from experts, would have viable saline aquifers, and as others have shown today, mineralization reservoirs throughout Brazil. But what's unique is there's a nice intersection in that area of a quite dense pulp and paper industry. So each of these dots on the map shows pulp and paper facilities. So a significant amount of existing biogenic CO2 that's already been built, ready to be captured, and the intersection of ideally viable storage within reasonable distances. And when we think about in the current market, based on what buyers will pay for CDR credits, volume needs, et cetera, and where the technology is at, we sort of think of three key criteria to make one of our projects successful, and that would be an existing biogenic source of at least 100,000 tons per year. We'd love to go smaller, but it's the economy of scale or diseconomy of scale starts to become challenging at that scale. And this is for biogenic CO2 sources, this primarily means pulp and paper mills, biomass power plants. It can be ethanol, although I think that's kind of an open topic of assessment amongst the broader scientific industry. Scientific collective is how the land use impacts and sustainability of the underlying feedstock is measured, and whether that's truly carbon removal or is it further reduction of a biofuel, given that ethanol's carbon intensity score is not, even with the most sustainable feedstocks, is not near zero. So that's a bit of a gray area for now. And then distance to storage sites at these volumes, we find that 50 kilometers of a dedicated pipeline is viable, perhaps even longer with larger volumes. So I think that's been a learning of ours, that we can stretch a little bit farther in distance than we may have expected. But very critical is to have a regulatory regime, not only for permitting of the actual site, but how storage is assessed, how the MRV requirements of the regulatory body outside of the CDR registries, and the process for leasing or acquiring pore space ownership. This is new, and there's a lot of aspects that can be similar and borrowed from oil and gas, but it is new, and that can take a lot of time. It really can, and it's a gating item. That's required first before project can progress. And then broad brush, before TNS cost, we find that the underlying point source capture cost needs to be in the $150 to $200 per ton range to attract off takers, sort of the all-in CDR price with TNS. And this is capture cost is mainly impacted by scale and utilities. So in that sense, I think it's quite easy to visual the inputs and outputs and assess what is likely to get built in the near term. Taking a similar lens for India, this is only showing saline aquifers. So one can imagine adding Bibas's map on mineralization potential, but there are quite clear clusters of pulp and paper activity, and some quite significant facilities. So I think there is a path towards anchor projects and establishing a cluster and sharing of resources and perhaps even pipeline networks to have quite significant carbon removal. And then to finish, I would repeat what I started with, that I think what's really unique about CDR is that it's not a physical commodity. It doesn't need to be transported from South America to Europe, and it doesn't require a domestic carbon regime. This really is more of a level playing field, and I think a now opportunity and quite unique within the energy transition.
Thank you so much, Taylor. I just want to remind everybody that you can submit questions in the Q&A. There are not a lot of questions right now, so I encourage you to do so. So last but not least, we have Sela, which is a company that deploys in situ mineralization in Kenyan basalts and integrate with geothermal energy resources. We are going to hear from Anastasia Wanjohi, and at Sela, she helps advance mineral storage solutions for durable carbon removal and sustainable energy transitions. Anastasia, I will pass it over to you.
Thank you so much. Apologies, I got late. I was in another very important and urgent matter I had to attend to.
No worries,
Yeah.
we're just on time.
I hope you gave out my my apologies for this. Yeah, I have a few slides, not a lot. I have quite a few though. And I just want to share some. Yes. So yeah, I'm supposed to be talking about our project at Sela. So let me introduce myself. I am Anastasia Wanjohi. I'm the project manager at Sela. We run a geological carbon storage project in Kenya, one of its kind, and we are a storage company. We have partners who are DACCS partners. Glad to see Sifa here, and some many other that we have. So Octavia is one of our very able partners. Excited to partner with them and excited to run the project with them. So I just want to talk about what we are doing in Kenya, where we are in our project, and how we've been able to actually integrate this with the geothermal energy or the geothermal sector. And I'll start by just introducing our project. So our project is located in the central Kenya Rift, along the greater Rift Valley that goes all the way from, Ethiopia, all the way to Zimbabwe and down. So we are somewhere in the central rift. It's actually a very active rift. And as you all know, the rift has a lot of geothermal potential. And we are among the first country. I come from a geothermal past. I worked in geothermal, and so I always like drum rolling for geothermal, even if they are not here. That we as a country are doing very well in terms of geothermal energy production. We are around number 6 in the world, and we are just about to join the gigawatt club, where we'll have people like US, Turkey, and the rest. And we are just about to beat our mentors, Iceland, which is really nice. We are doing better than our mentors. And yes, that is one of the reasons why we also thought of co-locating our project in the geothermal. Why? Because generally CCS is a very energy intensive project, and having geothermal around us is helpful. Why? Because we will be having our DACCS partners who use a lot of electricity, probably a little more than us. We also use a lot of electricity, and having a reliable electricity source is one of the things that we looked at. So we are co-located in an area that has a plant, 140 megawatts geothermal plant, and that will be generally for provision of steam and also for provision of energy. Our area is characterized by volcanic rock. As I said, it is along the rift. And as you all know, our rift is very active. So we have a lot of volcanic rocks, basically basalts, trachytes, volcanic ashes, and pyroclasts. But what we are looking for us for Sela, we are looking for the basalt rock, because that's the rock that essentially sequesters or does the reactions that you're looking for in terms of mineralization. We inject CO2, and then the minerals that in our basalts will release the cations, and the whole reaction space will happen, and carbonates will be formed, and they will remain underground forever. We expect them not to come back anytime soon. So just to go into where we are as a pilot project. So we are doing a pilot. We have ran extensive characterization studies, done a lot of geological studies, structural geology, resistivity, microseismic, geochemistry, all the geoscientific studies that you can think of. We ran them, and we did a model to be able to come up with the best site for us to site our well. What were we looking for? We were looking for basaltic rocks, and we were glad that you're able to get quite young rocks that are unfolded, unfractured. And we expect that without having so much, the rift is highly fractured, and but then we're lucky that our rocks are not as fractured as we had expected it to be. So meaning they are not also as hot. So in geothermal, we look for the hot place, but in geological carbon storage, you look for relatively colder areas. So we identified our site. We looked for all the permits that we needed. We were able to access our site, and immediately we started, we went into drilling. As you can see, is it on the left or on the, yeah, that should be, it's on my left. The rig is in place. So as we speak, we have drilled a well, and we have completed our well. We have fitted it with all the equipments that we require for us to do the injections and the tubing, the packers and everything. So we have completed our well. We have done logging for our well, injectivity tests, and we are happy with what we found. We are happy that we are able to actually have permeability for our CO2. After that, we then embarked on getting our CO2 system, a system that can be able to inject CO2 into the ground, and also a water system. Water system, for us, we are doing a different novel method where we are using WAG. That is, we are doing water and gas, water alternating gas, where we will be injecting some gas, and then we will follow it with a cycle of water. So we needed a system that is able to actually push both the water and the gas down. So we have constructed that system with our partners. We identified the contractors. We are able to get the kind of engineering we were looking for. We finalized our designs, and we have constructed both our water system and our CO2 system. Remember, our well is complete. So essentially, we are complete. I didn't put the photos of the site as it is, but it's complete. And as you can see in the middle, our labs are also complete. One thing that we look at Tsela is we are very keen on the MRVs, on the monitoring. We will be using geochemical isotopes to ensure and to check that CO2 has mineralized underground and that it has gone. That is where we are. That's the status of our pilot study. Let me call it also our scientific exercise, also I may say, because the main goal of this pilot is first to ensure that, to demonstrate that WAG can work, and it can work in basalts, and to demonstrate that geological mineralization as a concept can work. We have done that. As of a few days ago, we have tested our system. Our system is good to go. We injected a little bit of CO2, and we are happy with the results that we got. And yeah, I'm sure we will be announcing in a few days about what we found, the results of what we got, but we're very happy with it. Now, another thing to note and of importance is that the CO2 that we'll be injecting is actually from our partners. So we have been able to de-risk the transfer, the custody transfer with our partners. We have ensured that all the CO2 that we are getting from our partners is in the same characteristics that we require, all of them to be. We have already received CO2 from Octavia, and that's the CO2 that we will be injecting. So that will be a complete, cycle of DACC plus storage. And this will be a success story, in Africa, in the global south. And we are very happy that you're actually able to do this in Kenya. And I'm sure this has been mentioned. Some of the enablers for us to be in Kenya is we have rocks. Our rift is full of basalts, and we can sequester as much CO2 as we are able to do the wells. If one well is able to do our estimate and looking at all the information that is out there is about 50,000 tons of CO2. So you can imagine even the demand. Our partners are actually may not be able to meet that in even if we were to put a number of them together. So we have the capacity to actually store CO2 underground. We have the capacity to run this project. And after this pilot project, we will be now growing and expanding so as we are able to inject a lot of CO2. As I conclude, I just want to note that some of the benefits that these projects are bringing in, and I'm sure the other team members have talked about, is in the sector, in the carbon storage sector, we are able to show that this can happen. For us in Kenya, the reason why we choose Kenya is we have abundant resources, as I mentioned. We have for storage, we have the geology, we have the team, the talent. We have very talented people. For us, one thing that we have noted is that it's very easy for us to kind of use the same engineers that you're using in geothermal, which is a very mature ecosystem, and the supply and everything, it's easy for them to transition to serve us on the storage side. So we also have a clean grid. As we said, energy is one of our requirements, and also that our method will not be using so much water. So we'll not be using potable water. You're using just some borehole water that is a borehole which is not far away from us to do this. So in terms of the impacts that is going to have on the environment, we have looked at it. We have looked at the risks. As I said, we're also doing even the microseismic surveys in the area. We've looked at the impact that it has in the community, both positive and negatives, and tried to look at the mitigation, what we can do. We have talked with our community members. They are all very eager to actually participate in the project because the positives actually outweigh the negatives. The job creation, material production and supply and everything. So this is something that we really look forward to the project scaling and running a complete CCS DACCS plus storage project in Kenya. Thank you so much.
This is wonderful, Anastasia. Thank you so much. And thank you also to all our panelists. Now I will pass it over back to Jen and Shrey.
Thank you so much, Elena. I'm going to introduce my PhD student, Shrey Patel. Just a brief intro. Shrey has his bachelor's in chemical engineering from IIT Technology in Madras, India. And in Shrey's PhD research is using Aspen and also very, very fun, direct chemical engineering and incorporating carbon removals into existing processes. An example is looking at all of the data centers that are coming online and whether or not we can think about direct air capture coupling to data centers as pulling the heat away to cool them, and also looking at direct air capture coupled to clean hydrogen for sustainable aviation fuels with a focus on LCA and techno-economics. So with that, I'm going to hand it over to Shrey, And we are short on time, so we might only have time for one question, Shrey.
Thank you, Jen. Thank you, Jen. Yeah, I think we have seen three questions of I will pick one question which seems to be more directed to the panel, which was the first panel, and also this panel where we're talking about when there are what are some different trade-offs of storage in saline aquifers versus basalt when both are available. For example, in Brazil and India, there seem to be regions where both formations are available at different depths. And in that case, what considerations make one option more attractive than the other? And I would like if Dr. Vibhav Sen can start off, and the other panelists can join in as well.
Yeah, thanks, Shreya. Uh, uh, as far as the saline aquifers in India is concerned, we are yet to have a detailed understanding the disposition, the structure of these saline aquifers. No doubt, some first order information is already available in the western part of the country, in the Rajasthan, in the Barmer basin, but detailed study are yet to be done. Similarly, in basalt, the actually the problem is unless until you put some some barrels of CO2 inside the basalt, you really never know what is going to happen. All what we are doing is still in lab. We are hopeful that by this year we are going to have some facilities, at least pilot scale facilities in basalt, where we can put some injection and test whether they are really holding good as far as the injection is basalt is concerned. No doubt, like many of the speakers have touched upon, the different aspects, especially geological structures, are need to be considered. The fault system, the fracture system, the porosity, permeability, and there is whole gamut of problems which needs to be addressed when we are doing real injection. So there are a lot of challenges, but there is a lot of hopes also, because the basalt in India, especially the Deccan basalt, comes with a great thickness. You can have 800-meter thickness for thousands of kilometers. So the opportunities are there, challenges are there. So hopefully, the more research is needed, actual injection is needed, and a few test pilot drill holes in and pilot injection projects in both saline aquifers and basalt would really lead us to understand what is the real scenario is. Thank you. That has been a great question.
Thank you. In the interest of time, we'll keep moving on. There are two more questions, and I would encourage audience to ask more questions. And if the panelists can type their answers in the chat, that would be awesome. I would pass it back to Jen.
Thank you so much, Shrey. Next, we're going to move into our last panel. And I want to introduce my research associate, Dr. Abby Lundstrom. Abby holds a PhD in geology from the University of Southern California. And I would describe Abby's research as everything, including alkalinity with carbon removal, from oceans to rock weathering. And with that, I'll hand it off to Abby.
There we go. Can everyone hear me? Great. Okay. Thank you, everyone, for your great talk so far. So as we've heard, Brazil, India, and Kenya all have the resources and technical potential to deploy CDR technologies. Especially, we've been focusing on DACCS and BECCS, but other technologies as well. And they also have the entrepreneurial energy to build out these technologies on the ground. But scaling CDR also requires planning and coordination at governance levels to support this energy. So as we just heard from some of our speakers from startups, they need the right regulatory environments for projects to progress. So in this session, we'll hear from experts about the broader systems needed to facilitate deploying CDR at scale. We'll be looking beyond the individual projects or individual technologies to consider these enabling conditions and policies. So essentially, we'll zoom out to consider, as Jen mentioned, how do we build a CDR ecosystem, especially one that complements other mitigation strategies to reach net zero. So we're fortunate to be joined by three outstanding speakers on this topic. We had one speaker who unfortunately couldn't make it because of a a conflict at the last minute. But we have speakers who can speak across perspectives, national, regional, and international policies. And so our first speaker we'll be starting with is Fiona Mugumbi. She is a carbon markets advisor at GIZ, or the German Society for International Cooperation, where she supports climate action efforts in Kenya and East Africa. She's an expert in navigating carbon market opportunities in ways that are fair, transparent, and aligned with development goals. She was previously head of growth and partnerships at Octavia, and she is an engineer by training. So I will pass it over to you, Fiona.
Hi, just confirming if you can see my screen. Just let me know when you can see it.
Yep, it looks great.
Yep, it looks great. Super. Okay, cool. Okay. Good evening, everyone. It's good evening here in Nairobi, Kenya. It's actually 6:48 p.m. So happy to take you through this. So my name is Fiona Mugambi. I'm the Carbon Markets Advisor at JZ Kenya. JZ is a development corporation on behalf of the German government. So for us, our political partners are the Ministry of Environment, particularly for the project which I'm supporting, which is promoting climate strategies and NDC implementation in Kenya. Our political partners are the Ministry of Environment, Climate Change, Ministry of Environment, Climate Change and Forestry. So today I'm going to take you through just setting the policy landscape in Kenya, just taking you through the National Carbon Registry and the evolving governance framework for carbon markets. I don't know if my screen is moving. Okay, there we go. I hope you can see the next slide. Yeah, so across the continent, I guess the biggest challenge hasn't really been about the lack of mitigation potential, but really how do you structure carbon markets, especially with the rise of carbon projects, where from the government side, for them it's how do you track carbon projects through the whole project life cycle? How do you ensure there's integrity? How do you ensure these benefit sharing mechanisms? How can you properly account for projects in the voluntary carbon markets? How can you properly account for projects that want to get into the compliance market? So with what used to happen traditionally, you would find that projects, for example, would be submitted manually, and there's be a lot of big heavy files on one single project, and that would create a lot of timeline delays, not just for the government but also for project developers. And you'd find that there's really a lot of struggles in terms of data aggregation. So what is becoming increasingly clear is that carbon markets are not just financial instruments. They're now becoming policy-driven accounting systems. And what you'll find out is that for markets to function with integrity, you need at least three layers. You need policy, governance, and infrastructure. In policy, where you want clear rules on who can participate, what kind of activities are eligible, how the benefit sharing mechanisms, and under what conditions can credits be authorized for export. And when it comes to governance, the things you want to see is how do you review and approve projects through the whole development life cycle? How do you issue, with what conditions do you issue the letter of authorizations? How much will it be? How much budget do you have to issue these authorizations? And then I think lastly is how do you ensure also whatever you're issuing aligns with your national climate targets? Then I think the last bit on infrastructure, the things you're looking at is you're looking at digital systems, you're looking at the registries, you're looking at interoperability with the ICPs. And now with taking all of that into consideration, you're finding that the emerging approach is that we want to treat carbon systems as digital public infrastructure, and this is important because it reframes carbon markets away from fragmented project level transactions and towards a highly coordinated sovereign system. And I think the biggest outcome from this, I think these are common terms that you keep hearing in the carbon market ecosystem is, it ensures, there's transparency, there's traceability, and there's critically, there's data sovereignty. So with that in mind, now the registry, at least the National Carbon Registry, effectively structures now carbon markets into a set of governance phases that span the full life cycle of a project. Where it begins with project design and submission, where governments gain early visibility into the project pipeline, and then moves into national review and approval, where decisions such as the letter of no objection, letter of support from the counties, letter of approval from the government are issued, reflecting alignment with national priorities. Then coming from there, you now then move to when you get the letter of no objections, now you move into the government would want to see are these credits issued by the issuances under the ICPs, the independent crediting programs, and in what conditions or what baselines were used, what methodologies were used. Then from there, a letter of approval is issued. So what you find is that the Kenya National Carbon Registry is able to track all those different processes and really aggregate them into one single repository so that any project developer can be able to view all of this at a glance. The government as well can be able to view this at a glance. I think the most critical phase comes at authorization, where the government then decides whether credits can be transferred internationally under Article 6. So the registry tracks the transfer, use, and retirement of credits, and it ensures transactions are transparent, and that that any form of double counting is avoided. Again, Kenya's National Carbon Registry, when it was launched earlier this year, it was set out to ensure that there's registration, there's nationwide registration of all carbon projects from the voluntary carbon markets to Article 6.2 to projects that want to get to the Article 6.2 status. So for Article 6.4, projects do not need to be registered under this, but what the government is working on is ensuring that there's that form of interoperability with the 6.4 registry. Yes. So, I mean, you can think of Kenya's carbon policy approach as a sequenced build out of a full carbon market system. So it's not really more of one single policy intervention that can cover everything. So it has really been it's been really a stage-wise development process. So just taking you through the whole process, the Climate Change Act of 2016 is where the carbon markets were really first implicitly recognized in the Kenyan law. However, at that stage, there was really no detailed framework in terms of how carbon markets would function. So, and the real shift came at the confines of the Africa Climate Summit in 2023, where the act was amended, which now explicitly formalized carbon markets within Kenya's legal architecture. That's where, in that act, that's where you would hear things like the beneficiary mechanisms, the 40%, the 25%, and how that is going to be affected. How an annual social contribution is going to be enforced for carbon project developers who are either on public land or community land. So again, this is also where we begin to see key principles emerge, particularly around sovereign oversight and the benefit sharing and the role of government in authorization. So following 2023 and 2024, I think around May 2024, that's when the carbon market regulations were ratified. And it was then at that point now we started seeing more carbon market regulations coming into play. That is when we also there was the announcements of the development of the carbon registry regulation, trading and non-market regulations. So at least now for the carbon market regulations laid out really the schedule of how really the whole process of how do you apply for national approval as a carbon project. It also talks about who the designated national authority is, who has a policy oversight on carbon markets, and etc. So again, what we're now seeing is the finalization of this framework. The remaining regulations, including, so the remaining regulations, the ones which have been in development the whole of last year, those are the carbon registry, trading, and non-market regulations. For these ones are going to be gazetted in June of this year. Currently, they are with at the Attorney General's office. So importantly, the National Carbon Registry has already been launched ahead of full gazettement. This signals that Kenya is not waiting for perfect policy conditions; it is moving in parallel to build both the digital infrastructure and the regulatory framework needed for a functional carbon market. Again, all of this just reflects a deliberate strategy that whereby we first establish the legal basis, then we define the rules, and finally operationalize the system through the infrastructure such as the registry. Again, the sequencing is very, very much important because it reduces the regulatory risk while allowing the system testing and market signaling. Yes. So now building from that, what is very significant is that from Kenya's experience is not being developed in isolation. So GES and Kenya, what we're also working on after supporting the development of the National Carbon Registry is a development of the Africa Registry for Carbon. This is now really a broader effort to translate these lessons into into a scalable model through into a scalable model. And here what we want to ensure is that countries are not really reinventing the wheel in terms of the development of a national carbon registry. So the ARC toolkit now builds on the functional scope of Kenya's registry and extends it into a regional public digital infrastructure. So like the National Carbon Registry, this one doesn't really explicitly issue credits. Instead, it supports the registration of carbon projects in our country, supports the authorization processes under Article 6. It tracks mitigation activities in a much easier way that accelerates the whole NDC accounting. Also together with GHG reporting and national accounting. I think that what differentiates ARC from other open source registry solutions that are there is that it's modular, it's interoperable, and adaptable to national legal and institutional contexts. Yeah, and again, the Africa Registry on Carbon just provides a way to avoid starting from scratch. It helps countries reduce data fragmentation and also, again, accelerates readiness for participation in, Article 6. To sum it all up, I think it's very important to situate that this discussion within the broader evolution of carbon markets on, what's really the role for carbon dioxide removal. So in Kenya, as in many other countries, there isn't yet a dedicated policy framework specifically for removals. However, there is a clear openness from government to explore innovative CDR approaches. particularly as part of longer-term climate strategies. I think one of the hardest constraints CDR faces is national accounting clarity. And again, for removals to be meaningfully integrated into national climate strategies, they need to be properly accounted for within the NDCs. And that requires clear methodological guidance particularly from the IPCC and within the UNFCCC. And as my colleague in India also just mentioned, again, some of these methodologies and this reporting guidelines are going to be ready in a year or so. However, in the meantime, I think the government is still very much open to explore and understand what are these removal technologies, how do we govern them, and how do we regulate them in a way that is free and fair. So at the same time, the systems being developed now, from registries, MRV frameworks, and the governance processes are already laying the foundation to accommodate CDR as those guidelines evolve. Again, the National Carbon Registry does not discriminate whether, your project is coming from, removals, or it's coming from agriculture, it's coming from land use, it's coming from energy. No. As long as you're able to register your carbon project, mention which sector you're coming from, etc., then it's easy for you to, whether you're getting a letter of no objection or a letter of approval or authorization, it's easy for you to go through that system. So as it stands, it's not discriminatory in any way. Again, so what you're seeing again with Kenya being on the vanguard in deploying in terms of Article 6 readiness is we're also seeing that Kenya is very much open to innovation and coupled with caution driven by the need, for robust accounting frameworks. And this is again likely to shape how quickly and what scale CDR is integrated into national carbon market strategies. Yeah, I guess I'll just end it at that and just be on standby for any questions.
Excellent. Really impressive. Thank you for sharing about the experience building the framework. Thank you. So moving on to our next speaker, who will be talking about perspectives in India. So we have Varun Agarwal. Varun is a program research lead with the Climate, Economics, and Finance program at WRI India. He has worked in climate change mitigation research for over a decade, including work on low carbon development and decarbonization, carbon pricing, and just transition. He's previously worked with the Confederation of Indian Industry in the software industry and with renewable energy. He has a master's degree in environmental and natural resource management and a bachelor's in computer science. So thank you, Varun. I'll pass it over to you.
Thank you, Abby. And let me just share my screen. And if you could just confirm if you can see my slides.
Yes, we can see it. It's not in presenter mode yet, but we can see them. That looks great.
Okay, perfect. So yeah, thank you again for giving me this opportunity to speak here. My name is Varun and I work for WRI India. WRI India is an organization that works on the topics of at the intersection of economic development, nature, and climate change. And in India, our work is organized into 5 different program verticals. One is, I work for the Climate Economics Finance vertical. We also have an energy, a food, land, and water, a cities team, as well as a transport team, which looks at all of these issues thematically. I just keeping an eye on the clock. I'll try to keep my slides presentation short. But just with the caveat that, as Abby mentioned, I'm not really a CDR expert. I've mostly been working on the issue of climate policy and looking at India's greenhouse gas emissions going into the future with the help of frameworks like modeling tools. So I'll just sort of take my remarks on CDR with a bit of a pinch of salt and just sort of correct me if I go wrong anywhere. So just to begin with, why are we talking about CDR? Sorry. I hope you can see the slide again, right?
Yeah, we see the one India's climate commitments and projected greenhouse gas.
Yeah, okay, perfect. Yeah. So if we look at India's emissions, India emits currently about 3 billion tons of greenhouse gases annually. And if we look at India's emissions in a reference scenario that considers India's current policies, we see that India's emissions by mid-century would approximately double. This is despite India's energy intensity per economic unit of economic output reducing by about 50% over this period. And that really highlights, like a lot of the countries in the global south, India's sort of problem that despite a lot of improvements in energy efficiency and energy intensity, it really doesn't translate into a reduction in absolute emissions because of the pace of industrialization, economic development, and urbanization. If you look at the emissions by sector, we see that really the industry emerges as the largest contributor to India's future emissions and comprises, this is the portion in gray on the chart, and comprises about half of national emissions when we look at the total emissions in 2050. The other noteworthy fact in this chart I just want to highlight is the fact that India already has a significant carbon sink in its land sector, which is about which provides a negative carbon sink of about 300 million tons of carbon dioxide per annum, and that's really something that's also relevant in the context of the subsequent slides that I'll talk about. India has both short-term and long-term targets to address climate change. The short-term targets largely focus on the electricity sector, which is actually the portion in yellow on the chart on the left, which is why you actually see that even over time, electricity sector emissions are by and large flat and they don't really increase, unlike the industrial emissions. India also has a net zero emissions target by 2070. And to put this into action, it's identified 7 pillars in its long-term low emissions development strategy, which it submitted to the UNFCCC. That, of course, includes sectoral pillars to decouple emissions from growth in the power, industry, transport, and building sectors, but also cross-cutting pillars for scaling up CCUS, forestry, and climate finance. So the point to note is that CCUS and land-based removal, specifically forestry, has been mentioned in India's LT-LEDs. If we look at why CDR matters for India, the charts here just illustrate what would happen to Indian emissions in a very ambitious decarbonization scenario. So the line in black represents the current policies of the reference scenario, which I was showing earlier. And through one of our models called the India Energy Policy Simulator, we also constructed a scenario called the long-term decarbonization scenario, which assumes ambitious uptake of renewables, green hydrogen, and electric mobility relative to the reference scenario. And what we see is that despite even if such policies are implemented to their sort of theoretical potential, emissions in this scenario don't really go up go anywhere close to zero. Looking at something like industrial emissions, what India can hope for, even in an ambitious climate action scenario, is see a flattening out of emissions to current levels by 2050, as opposed to a reduction. So in sectors like the industrial sectors, in which India's emissions, also 60% of industrial emissions actually come from hard to abate sectors like cement and steel, there is a high likelihood of residual emissions despite ambitious mitigation, which makes CDR an important consideration in the context of long-term net zero strategies. Land and bio-based CDR in India is already a focus of existing policy commitments. For example, the point about the carbon sink through forest cover that I mentioned is already acknowledged in India's NDC reporting and targets. And there is also a push on afforestation policies from other perspectives of biodiversity conservation and so on. So this is well recognized, and there's a strong focus on this. India also has a large potential for geological storage, yet to be tested, but preliminary estimates indicate a range of 400 to 600 gigatons in underground aquifers, as well as basalt formations. So all these make India sort of a good case for CDR in the long term. If you look at the current CDR landscape in India, I've just tried to categorize the different CDR methods in 4 categories. So if you look at land-based CDR, which basically constitutes carbon sinks through natural forest cover, India already has policies to increase its forest cover. India recognizes the role of forests also as carbon sinks, and recognizes this both in its NDC and long-term strategy targets. And it already has several policies to protect and increase forest cover, which are, again, not all from a climate lens, but also from other lenses, like a biodiversity lens, like the Green India Mission, the compensatory afforestation policies, and so on. Then if we come to a bio-based CDR, which would include biochar and BECCS, there is emerging sort of developments here. Mostly, these developments are policy adjacent. In the private sector, there has been a lot of interest in biochar, especially due to the large biomass base and agricultural residue availability in India. Recently, an Indian company called Varaha struck a deal to supply 100,000 plus tons of CDR credits via biochar in India to Microsoft and Google by the early 2030s. So this is an area where there's a lot of potential in India. The private sector has already recognized it, and where there's demand from international or voluntary demand from international markets, there has been some activity has begun, but not really anything significant on the policy front. If we talk about industrial CDR, again, technically BECCS is the CDR method. Currently, the policy focus has been on CCUS, which is a prerequisite for BECCS. These policy developments have been very recent. Like I said, this is the CCUS policy in India at the moment is really framed as an industrial decarbonization policy for the hard to abate sectors, not necessarily carbon removal. The recent developments in this regard have been that the Department of Science and Technology of the Government of India last year released at the end of last year, released the CCUS R&D and scale-up roadmap, which basically identifies use cases in different industrial sectors for CCUS. And in this year's union budget, we saw an allocation of 20,000 crores, which is approximately 2.1 to 2.4 billion USD over the next 5 years, to sort of scale up some of the CCUS pilots in the industry in line with the DST roadmap. So at the moment, in summary, there's a sort of focus on CCUS, but not really on removal, but still in very early stages. And if we talk about things like DAC or enhanced rock weathering, at the moment, this is really not being spoken about in India. So if we just sort of splitting the previous slide into a method-wise outlook, in the near term, I mean, forestry is already providing India's largest carbon sink. There are many policies on this front, including domestic policies and NDC targets. However, I mean, the challenge in terms of expanding forest cover is really land use competition with rapidly urbanizing land. India also has targets for biofuel use in the transport sector, and goals of food security and sort of scaling up renewable energy on a very, very large scale, which is more land intensive than traditional thermal and fossil fuel based energy. So one thing that's being increasingly recognized in the policy discourse is sort of increasing demand for land use going forward. And that's going to be, I think, the main determinant in terms of the scale up of this afforestation policies in the medium to long term. Biochar, like I said, it already has a very strong alignment with crop residue policy and air pollution goals in India. There's also interest from the private sector due to demand in such credits from international buyers. But at the moment, there's no direct policy support for this. The clear challenge in this regard is going to be, I think, at the moment is the lack of monitoring, reporting, and verification. There are no clear standards to regulate or to establish the credibility of such removals in India, as well as the lack of domestic markets. So the interest in the private sector has come due to the demand from international markets. In the medium term, there is a good possibility for BECCS in India if the carbon storage infrastructure develops according to the recent policy push that is sort of trying to do this. Like I said, there is a large potential for BECCS in India, both because of large biomass availability as well as sort of large storage potential. But due to the recency of the CCUS policy, really the suitability of the storage infrastructure really needs to be tested and scaled up first. So if the CCUS policy addresses this successfully in the medium term, BECCS could also become a feasible option at scale for a country like India. And in the long term, I mean, of course, India could look at other solutions like DAC and ERW as well, but at the moment, there's really nothing to say about them in the Indian context. So if just to summarize what I presented, India clearly has supply side advantages for land and bio-based CDR. There is a large biomass base, huge amount of agricultural residue, which is currently often not utilized for any economic purpose and just burnt, also contributing to India's air quality problem. So addressing this also has clear co-benefits in terms of air quality goals. Labor costs are low. There's also private sector interest in monetizing some of this. However, like I said, there's a need for MRV standard and development of domestic demand to really scale this up to the next step. But there is possibility for this in the short to medium term. There's already an emerging policy push for carbon storage, which is going to be a prerequisite for BECCS or direct air capture, but it's still very early days. While there's significant theoretical potential for storage, site characterization and testing will hopefully now start in this decade due to the recent policy budgetary allocation in the national budget and policy supported pilots. However, there is still likely to be an infrastructure gap because the existing funds of allocation of public funds is likely to be insufficient. So at the same time, while this is encouraging, we do need integrated policy as well as monitoring, reporting, and verification standards. So like policies exist, but often their goal is not CDR, but they serve other policy goals. So in that sense, there are policies that exist in this context, but usually fragmented and for other purposes. It would be good to sort of integrate all of these policies into a national CDR strategy, so that the complementarities and the policy gaps can be clearly identified in the context of scaling CDR over the near, medium, and long term. There's also an urgent need to develop domestic MRV standards. Even if sort of these things take some time to scale up, early development of standards can help ensure credibility, sort of increase international demand, and thereby scale up private investment. And there's also scope for integrating sort of the CDR policy with other domestic policies. For example, another policy that's emerging in India is India's own domestic carbon market, or the carbon credit trading scheme, as it's called in India. While it's still early days for this scheme, they have already notified some of the targets for sectors like cement, steel, and other industrial sectors. And the general consensus by looking at these targets is that the targets are relatively weak. So the effective carbon price that will develop in the market as a result of these targets will probably not be enough to incentivize private investment into these capital intensive technologies or capital intensive investments like carbon storage. So there's also a need to sort of look at the ambition or the relative strength of these policies from a CDR perspective to really see what it would take for such policies to incentivize private sector investment to be able to scale CDR. Yeah, with that, I'll just stop. Yeah, thank you very much.
All right, thank you so much, Varun. We are approaching the end of our time, but we definitely have time for our last but certainly not least speaker. So I'd like to encourage everyone to ask questions. We'll definitely have time for a question or two for this last session. And our last speaker is Emily Ann Dionisio. She is also at WRI in Brazil. She is a greenhouse gas accounting specialist, where she works at the intersection of climate, land use, and corporate decarbonization. She advises public and private sector leaders on greenhouse gas emission reduction goals, including the integration of nature-based solutions. So she has a bachelor's in biology and a master's and PhD in applied meteorology. So I'll pass it over to you, Emily. Thank you.
Thank you so much, Abby and Jen, for the invitations, and all colleagues for Kleinman Center for opportunity to be here today. Can you see my screen?
Oh, looks perfect.
Okay, awesome. So thanks for the introduction also, Abby. So I will be trying to be very briefly. So Brazil has committed to climate neutrality by 2050. As like stating their NDC. And we use like Brazilian land use and energy system model, which is like an integrated assessment model to set this target. And once the results of this model show us that Brazil will depend like carbon removal to achieve their climate neutrality by 2050, especially 2040s onwards. So technologies as like BECCS and other negative emissions are expected to play like a very important role. But at the same time, this is a very sensitive topic in Brazil. So there is a concern for some civil society parts that technologies like carbon capture storage or carbon capture storage and use storage could be like a substitute for mitigation. So let me be very clear that for WI, we see CDR as like a complement to mitigation, not a replacement. And our goal starting this agenda here is ensure that Brazil is prepared for example, regulatory framework, scientific research, technical capacity, and working this agenda, we hopefully support Brazil achieve the climate targets, reducing emissions around 2.5 gigatons of CO2 to 1.2 by 2030 and achieve climate neutrality by 2050. If you look for this slide, we will see that Brazil has a very different emission profile compared with most of the countries, as also Varun showed now about India. So today, emissions in Brazil are largely driven by land use change and agriculture, but future scenarios show us that we will have a major shift, and land use change goes from being like a net emitter to a net sink, especially due to zero and reduce deforestation and increase of restoration and land and nature-based solutions. So emissions from industry are projected to rise by even when mitigation plans are taken into account. So projections of GHG emissions from energy sector, for example, in this slide show us that only the energy will have increasing 19% related in comparison with 2024, and that in the future by 2034, 68% of the emissions will be related to industrial and transport activities, which really reinforce that CDR action method in Brazil will be increasingly necessary to achieve climate neutrality alongside nature-based solutions. So in Brazil, why CDR is an opportunity. So Brazil has abundant natural resources, large areas of land, a strong renewable energy matrix. So nowadays, 89% of the energy matrix of Brazil is hydropower. And we also have been seeing a lot of important progress in terms of political institutional support for CDR. So we had last Friday, March 13, Brazil launched Plano Clima, the National Mitigation Plan, which explicitly mentions carbon capture and storage as a strategy to Brazil move towards decarbonization. And we also have Nova Indústria Brasil, which is a policy that supports long-term investments in decarbonization and innovation pathways for industry. So together, these both policies creates a strong foundation to scale up CDR domestically and support the design of more regulatory frameworks, investments, as well developing a capacity building programs. And also in context of COP30, as you know, last year we had COP being set here in Brazil, in Belém, and it was the first time that we had a space in Blue Zone to discuss CDR opportunities. And once Brazil is leading this process towards COP31 in Turkey, this is also could be a good opportunity to promote dialogue on the need for CDR in diplomacy and multilateral efforts. So this slide I want to highlight the main opportunities for Brazil, but I think we covered very well here in this workshop, the opportunities for energy, also for bioenergy. Nowadays, energy alone emits around 400 million tons of CDR, so of CO2. So sectors like steel, cement, and fertilizers will continue to grow. So it's strategic for Brazil have CDR supporting these sectors. For bioenergy, I don't even like mention because we talk a lot about geological storage capacity, availability of biomass, waste. What I want to highlight here is like biochar and enhanced rockery weathering. As a country, a tropical country, these nature-based and hybrid like CDR solutions are very interested for us. So Brazil has a lot of like residual biomass, not only sugarcane, but like rice, rusk, forestry reduces that could support the development of like biochar in Brazil. And both of these two technologies also support and provide a lot of co-benefits, social and agriculture. So this could like include family farming in different many biomes, improve agriculture productivity, improve support circular economy. And nowadays in Brazil, a biochar is already operating like in a scale. So we have a lot of companies like Net Zero, Aperam, providing carbon credit, if I'm not wrong, something around like 6,000-7,000 tons of CO2 per year. And in enhanced rockery weathering, we also are like early stages, but last year we had the first company delivering like carbon credits using isometric verification. In terms of the political support, like I mentioned, we had launched last week the National Mitigation Plan, which supports CDR technologies, especially carbon capture and storage, incentivize BECCS and other negative emissions, and have some priorities that are very interesting for us. For example, for the energy sector, one of the priorities for Brazilian government with this plan is enable carbon capture use and storage technologies through regulatory incentives and support research and development and innovation, advance negative emissions, especially for BECCS, via considering like integrated planning, infrastructure development, and for industry, between the priorities are promote more circular economy, reduce industrial carbon footprints, and deploy carbon capture, use, and storage to abate the process emissions. And for agriculture, we have like a mandatory, which is like reinforced by the government, is that promote more sustainable and resilient agriculture practice, which is really related to biochar and enhanced rockery weathering. We also have the National Industrial Decarbonization Strategy, which was like in public consultation last year, and we expect it to be approved soon. That also recognized CDR as a technology, relevant technology, and in short-term action by 2026, consider like conduct comparative studies on regulatory gaps between Brazil and other more advanced decarbonized economies. And at least, but not less important, like I mentioned, Nova Indústria Brasil, which is a policy that prioritizes CCS and BECCS and low carbon hydrogen. And we have like $130 million dedicated for innovation and industrial decarbonization in Brazil. Other two policies that I can mention here very briefly is like the National Fertilizer Plan and National Bioinputs. The first one has as a goal reduce the Brazilian dependence for imported fertilizers, like strengthening domestic production. And the second one is like replace chemical inputs, fostering innovation in sustainability in agriculture, which is also really good. And if we are talking about biochar and enhanced rockery weathering. So regulation, I bring three main regulamentations in Brazil that are important in context CDR. First one is like the Fuel of the Future law, is like the first CCS law in Brazil. So this established like the National Petroleum Agency as regulator of this CCS activities, authorizing like capture transport projects. In November last year, they started like a public consultation about to start to develop more technical regulations inside the context of this law. We had in 2024 also the Brazilian emissions trading system law approved. So this law established like the Brazilian emissions trading system to create is like a foundation of the regulated carbon market, setting emission limits for some entities emitting over 25,000 tons of CO2 per year. And the idea, they will like determine and describe how to deliver and how to deliver like removal certificates, which will be central to integrating like CDRs such as like BECCS, DACCS, ERW, Biochar as tradable assets to the compliance system. And these have like a phased implementation. So hopefully by December 2026, we'll have determined like the allocation and eligibility methodologies to have this market working in Brazil. This law also established the necessity of like a permanent technical advisory committee, which is WR Brazil is part of it in the person of Karen, our climate director. So she participates for this permanent committee. And we also have a law very interesting about soil remineralizer. So it's like the first world law which like regulates a soil remineralizers and provides like maybe the basis for enhanced rock weather in Brazil. Although the accounting rules to consider carbon is not developed yet, but hopefully it will be in the context of Brazilian emissions trade system. So the just key takeaways. So like I said, concluding for in my speech, so Brazil has like a very unique opportunity, but we need to act like to close this gap between policy and implementation. We need like to build the foundations, like clear rules, participating in the process of develop MRV, crediting like a liability to unlock more investment and scale these technologies. And this requires collaboration. So it's why we are working this agenda. So trying like to, across government, industry, and civil society, support and shape a more credible and trusted ecosystem. And if you get this right, I think Brazil can not only meet their NDC, it's their NDC, but also lead the global CDR agenda. Thank you so much.
Thank you, Emily. Wow, it's exciting to hear what's happening in all three countries. Very early days of this industry, and setting the stage correctly is important. I'm going to pass it over to Aline Uwase, who is a third-year PhD student in our lab, the Clean Energy Conversions Lab at University of Pennsylvania. Aline is a chemical engineer, and she will be handling the Q&A.
Thank you, Abby, and thank you so much to our speakers. We only have time for one question, but for the other questions that I want ask, if the people could please reply in the chat, we'll really appreciate it. So just go with the first one we got. It's a question for Varun. So from a policy perspective, is there any particular CDR pathway that's preferred or getting more research funding? It seems CCUS may be a priority for now, but how about ERW or biochar pathways, which may have direct community co-benefits?
Yeah, thanks. Thank you. Just very briefly on this. So CCUS, we don't generally consider a CDR pathway. It's a prerequisite for CDR because CCUS by itself doesn't really remove carbon dioxide. It's just necessary for having, for example, something like DAC or BECCS. You have to have carbon storage. So I think at the moment the policy developments in India, we only have policies for land-based CDR for enhancing our forest cover. And as far as the CCUS developments are concerned, I consider them to be CDR pathway agnostic. It's just sort of we are laying the groundwork for, being able to do BECCS, which we can do because we have large biomass potential, or in the sort of long-term future, direct air capture, if that's feasible. But we can only do that if we have enough proven storage capacity. At the moment, it's just theoretical. Yeah, like I said, for biochar, there's already interest from the private sector, and that's really happened because of demand for such credits from international buyers, voluntary corporate buyers mainly. And that's just because of the economics of the biochar market in India. We have a large sort of volume of agricultural residue. At the moment, there's no real sort of mechanism to assign a value to it domestically. It's mostly just discarded, burnt, or goes to the sort of decomposes organically. So that's why sort of the private sector started tapping into it. But in the near term, I think this is also one opportunity where policy can really try to streamline this and create a domestic market for something like biochar, which can help scale up using the near term. Yeah, thank you.
Thank you so much, Varun. Can we ask one more question, or are we over?
I think we have to wrap it up.
Okay, thank you to our speakers.
Well, and I just want to say thank you to Aline, and I want to highlight that Aline is actually from Rwanda, and also been really closely coordinated with WRI in Rwanda too, which is kind of also part of this global community. And I also just want to mention that Aline's PhD research in chemical engineering is on characterization of micro and mesoporous materials for carbon removal applications spanning mineralization to biochar. And with that, I just want to thank you, Aline. Thank you for my team for helping to moderate today. And we are at time, but remember everybody, there's a recording of this. So if you had to drop off early, no worries. I just want to end by saying what we're seeing in today's webinar is exciting. These ecosystems are already beginning to take shape. We look forward to continuing these conversations with academics, industry partners, and policymakers through future webinars. And we'll keep you all connected on that, watching progress across the space, expanding this network as we work together to build a more connected, global and globally informed carbon capture and carbon removal ecosystem. The future of carbon removal won't be built in one place. It's going to be built through many regions learning from each other. So thank you all for joining us today, and have a great rest of the day.